Hello. Start video. Yeah. I'm alive, Gregory.
Can't see anyone. Can you see anyone? Can you see anyone?
Well, I don't know what I'm doing here.
Yes, good, Roy. I can see you.
Okay, it's must be retarded a lot because I'm talking at the moment and my mouth is closed on the screen. So,
Okay. No, you are talking and I can see you speaking.
okay, then this must be out of date here.
Can you see anyone?
Well, I don't know what I'm doing here.
Yes, good, Roy.
Yeah.
I can see you.
Okay, it's must be retarded a lot because I'm talking at the moment and my mouth is closed on the screen.
No,
now I'm
you are
talking on the
talking and
screen.
I can see you speaking.
Okay, then this must be out of date here.
Can you see anyone?
Roy, can you hear me? Yes, good, Roy. I can see you.
Okay, it's must be retarded a lot because I'm talking at the moment and my mouth is closed on the screen.
No,
now I'm
you are
talking on the
talking
screen.
and I can see you. There is quite a lot of delay.
I'm going to say something again. This must be out of date here. It keeps repeating.
Can you hear me?
Yes, I can hear you and see you.
Good, Roy. I can see
Good
you.
morning.
Vedi che la voce ritorna tardi. Dove sono gli altri? C'era Dimitrios.
Say something again. This must be out of date here. It keeps repeating 10 seconds. Yes, I can hear you and see you.
Vedi che la voce ritorna tardi. Vedi? Dove sono gli altri? Avevo mandato lo stesso in ritardo. I am having coffee.
Yes, I can hear you and see you.
Rashid, good morning.
Good morning. I was unable to to see you, but now everything is fine. I was waiting for 15 minutes or 20, I don't know. But now I see you, I see Roy. Nice to see you, Roy. Do you hear me?
Roy, can you hear us? Coffee.
Good. Yes, I could use that.
Oh, Peter.
Rashid, good morning.
Good morning. I was unable to to see you, but now everything.
Where is Dimitrios?
I was waiting for 15 minutes or 20, I don't know. But now I see you, I see Roy. Nice to see you, Roy.
Yes, I am 25 seconds slow on the screen.
Yes, very interesting. We are not in the YouTube flow, I hope. Maybe it's YouTube flow. Good morning. I was unable to see you, but now everything.
The
Where is
reason
Dimitrios?
I am 25 seconds late.
Dimitrios is still in the test Zoom. I saw him there in the other link.
Which other link?
Yeah, the other link, the test link.
In the?
Now there are two links. This one here for the meeting, and another link. Gregory can explain that for testing.
Oh, I see. I
It was
see.
open up at 7:30, and I saw Dimitrios in that link.
Okay. For the testing.
Dimitrios is still in the test Zoom. I saw him there.
Tell
In
him,
the other link.
tell him to come in this one.
Yeah, the other link, the test link.
In the?
Now there are two links. This one here for the meeting, and another link. Gregory can explain that for testing.
Oh, I see.
It
I
was
see.
open up at 7:30, and I saw Dimitrios in that link.
Вот я вас, вы извините, но я вас не вижу. Вот это достаточно интересно.
Dimitrios is still in the test Zoom. I saw him there.
Вот сейчас
Tell him,
The other link.
tell him to come in this one.
Yeah, the other link, the test link.
Yeah. Well, what do I do?
There are two links. This one here for the meeting, and another link. Gregory can explain that for testing.
Oh, I see.
It was open up at 7:30, and I saw Dimitrios in that link.
Okay.
Roy, apparently there is feedback on your computer, and
Okay.
maybe you can put some earphone, will be easier
What?
to put some
I'm
earphone.
going to shift to another computer. Close this bloody thing down.
Remo, Lavочkin people cannot enter also.
Now they enter, Rashid, everything is, they should be
Oh,
coming.
now I see them and Tiki. Excellent.
Yes. Okay, because I was looking for names, but they are of the person, but they're connected with the organizational name. Okay, everything is okay.
Okay, great that you were able to connect them. Excellent. I see people from IKEA. Very nice.
Нас наконец-то видно.
These are very brave people because there is in Moscow huge increase of amount of ill people. And now I see Lavочkin, also great. They're very small, but I see them. Hello, Lavочkin. Good. Oh, this excellent.
Yes, but Roy is not on the screen. Christodoulou is not on the screen.
Kerr sta provando un altro computer e Cristodoulou non ha i permessi ancora. per parlare.
Christodoulou non ha il permesso per parlare.
Non è tra quelli che risultano col permesso. E poi manca Tuft
E Tuft.
e Peter Fredel.
Okay. Can you hear me now?
Titus, you are there. Okay, good. Good news. Where are you? Yes, I can hear you very well. Can you hear us, Dimitrios? Dimitrios, can you hear us? You have the audio off, Dimitrios. turn the audio on, if you can hear me. Dimitrios.
Lui ha proprio la cornetta disattivata.
Dimitrios, you have the link to the voice off. Hello? Where is Kerr?
Kerr si stava collegando da un altro computer, ha detto, dove non aveva i problemi dell'audio, quindi il tempo che si riconnette. Ora si sta collegando qualcun altro.
We're still off the Roy. Good. Let's see if Roy.
Unmute, start video.
It's okay, Roy. We can hear you.
I'm current.
We can hear you very well. Gerard is off. Dimitrios is missing.
Okay. Demetrius. Am I on in action now?
Yes, you are in connection. Gerard is in connection. And Dimitrios has the missing the connection.
Okay.
Dimitrios, Gerard, can you hear us? Yes?
Excuse me?
Yes, you can hear us. Good.
I can hear you, yes.
Yes.
Good. I can hear you too, Gerard.
Good. Do you hear me loud enough?
So I can.
I think while we are waiting for Dimitrios, we can start the ceremony. And in this case, welcome to everyone. Well, it is a great pleasure to start this MG16 in direct all over the world. And we start with the traditional ceremony of the awards. We are still missing the connection for Dimitrios Christodoulou, but in the meantime, we can start with Gerard, and I would like to have Roy to introduce the presentation of the test award to Gerard. We have the box, and if you will come to Pescara, the better. We will give you honorary citizens, but otherwise we will send to you directly to Netherlands.
Well,
Okay.
it gives me great pleasure to announce the awarding of this to Gerard for his persistent devotion to the study of the quantum field theory boundary conditions at the black hole horizon. This is one of the great problems that has been worrying everybody in relativity for a long time. And Gerard is one of our hopes for solving this problem. I'm sorry, but I've really been knocked out of my stride by this attempts to get connected. Now, Professor Gerard has been a full professor at the Utrecht University since 1977. Nowadays, he's an emeritus professor at that university, but nevertheless, he has been traveling around the world and giving us all great talks and advice on the problems of physics. So it gives me great pleasure to award this trophy to Gerard.
Well,
I was very interested to see that Gerard had looked at the problem of the Maxwell extension of Schwarzschild and had noticed that there were different ways of connecting at the boundaries, especially with a twist.
and well, I recollect personally an event which happened at ICRA on April 30, 1999, when I invited Gerard to come to Rome to discuss a boundary condition for a quantum field on the black hole horizon. And this topic was discussed with Thibault, and it was very nice to see the point of view of Gerard. We have traditionally in ICRA, as you can see maybe in the poster that we have done, we have a tradition that all distinguished scientists visiting ICRA put their signature on the wall with an idea, a present for their visit. And this was also the case of Gerard. And I have reproduced in the booklet the signature that he put on the wall. But that was a very, very special visit because we had very limited amount of funds. Therefore, we could offer him only a round trip ticket, spending the weekend in Rome. It was cheaper. Therefore, he came on Thursday, he stayed all the weekend, and he went back on Monday morning. And this was a splendid visit, the period in which Rome, the spring, is the best time. And it was very interesting that during that weekend, we discussed a lot about, we leisurely discussed, and he pointed out that in our original paper with Dimitrios, there was a typing error, and there was a 2 missing in that mass formula, but that was just a printing, which we correct later. The following October of this year, Gerard received the Nobel Prize. And we were thinking about that, and certainly he would not have agreed to come after this recognition to Rome with a cheap flight. But anyway, it gave us the opportunity to send a wall, to discuss, to correct the number, and to have the joy to spend with him a splendid spring vacation in Rome. We are very happy to, therefore, recognize and give this motivation that Roy just called on for his personal devotion to the study of quantum field theory boundary condition at the black hole horizon, and look forward for his discussion tomorrow. Gerald, maybe you can say a few words.
Yes, indeed. Let me express my gratitude. Thank you, Roy. Thank you, Remo, for your kind words. I'm indeed very much honored. I had the impression that many researchers are just ignoring my findings about the black hole horizon and the topology of its boundary conditions. But apparently the organizers of this Marcel Grossman meeting, in particular Remo, did pay attention. And I will say more about my most recent ideas tomorrow afternoon. So the first time I went to one of these large gravity meetings, that was General Relativity number 8 in 1977, I was highly impressed. More than 1,000 participants, just like now. I thought the laws of gravity were by now well understood and documented, so what are those thousands of people doing? But the answer is obvious. There are very many observable phenomena where gravity in one way or other plays a decisive role. And so if you want to represent all those subjects as well, then 1,000 participants is not so many. But then I was shocked again. More than half of these people were investigating quantum gravity. Now, at that time, there were no observable phenomena at all associated to that. There are a few somewhat dubious things you can think of now. So what are all these hundreds of people doing? Well, just like me, they were speculating. One speculation even more absurd than the other. And that's still the situation today, 45 years later. Indeed, I think the number of solid results in quantum gravity can be counted something like on one hand or so. But speculate, everybody can do that. So what justifies this activity? I think the truth is that quantum gravity is notoriously difficult. Making a meaningful contribution to our general scientific understanding of this subject is extremely hard. And from my perspective, indeed, tangible progress is extremely slow. But I beg you, please be patient. We only uncovered perhaps a few % of the technical details of a solid quantum theory of gravity. But I am sure the rest will come one day or other, but it will come slowly. So I want to thank you again for this beautiful reward, in particular Remo, but also the others who have been giving this to me. Thank you very much.
I see that Dimitrios is online. Can you hear us,
Yes.
Dimitrios?
Yes. I can hear you. Can you hear me?
Yes.
Yes, we can.
Yeah.
Roy, then
Okay.
proceed.
Okay. Just getting it up here. This award to Professor Dimitrios Christodoulou is for his many lasting contributions to the foundation of mathematical physics, including the dynamics of relativistic gravitational fields, notably for contributing in 1971, at the age of 19, to derive with Remo Ruffini the mass energy formula of black holes as a function of their angular momentum, charge, and irreducible mass. Christodoulou subsequently turned to the study of partial differential equations and mathematical physics, to which he remained dedicated for the rest of his career. Highlights in this area include the theoretical discovery of the nonlinear memory effect of gravitational waves. This was published in a PhysRev letter. The monograph in collaboration with Sergiu Kleinerman on the global nonlinear stability of the Minkowski space-time. The monograph on the formation of black holes in pure general relativity by imploding gravitational waves, and the monographs on the formation and further development of shocks in fluids. It's with great pleasure that we give this award to Demetrius.
Yes, thank you. Can you hear me now?
Yes.
Okay. Yes, it is indeed an honor to be awarded this Marcel Grossman Award, and in particular, a special honor to be given the award by Roy Kerr himself, whose solution I consider to be the crowning jewel of general relativity. When I was about 17 years old, and I was a fresh graduate student at Princeton, John Wheeler, our professor, he encouraged his junior associates, like the assistant professors like Remo Ruffini, and all the graduate students to study the Kerr solution. And for some years, we were indeed all of us quite taken by this solution. We admired it greatly, and we tried to unlock some of its secrets. And to this effort, one of the fruits in this effort was the work and in connection, in particular, also with Remo Ruffini, with the mass energy formula, which came out when I was about 19. Then a few years afterwards, 7 years after, with the help of Madame Choquet-Bruhat, one of the past awardees of the Marcel Grossman Award, I turned to the study of partial differential equations and mathematical physics, to which I have devoted the rest of my career. Perhaps 25 years on general relativity and maybe 20 years on the fluid mechanics of compressible fluids. Well, I should say here that the two share something, because the Einstein equations and the Euler equations of compressible fluids both have the characteristic of being nonlinear systems of hyperbolic type. Of course, from some point on, they have other basic features which are completely different, and this leads to completely different phenomena. Well, at that point, the first important problem that we addressed was the stability of the Minkowski spacetime. I should say that coming back to the Kerr solution, that for many years after this work that I did with Remo, there were much more study of the geodesics in time-like and null geodesics in the Kerr solution, which is also illustrated by the sculpture which represents the award, and also by work on the behavior of linear field equations on Kerr, in particular also by Chandrasekhar, Tchaikovsky, Whiting, and other people. And this was somehow thought to be in the framework of the stability of the Kerr. However, at later in time, when I was working on partial differential equations and mathematical physics, Sergio Kleinerman and I decided to study a simpler problem, namely the stability of the Minkowski space-time. Of course, from the linear point of view, this is completely trivial. But the point was to to study the evolution of small but finite departures from the initial departures from the Minkowski space-time. And this is not trivial and led to this work. I should say that the corresponding problem in the context of the Euler equations of compressible fluids has a negative answer. That is the analog of Minkowski space-time is a fluid which is at rest in some Galilei frame at constant temperature and pressure. And if you make a small but finite perturbation in a fixed ball in space, then in fact the solution does not exist as a smooth solution for all time, no matter how small the perturbation is, but you wait long enough and the shock will form, destroying the smoothness of the solution. After this, I turn to another problem in general relativity, which was in fact given to me by Professor Wheeler even earlier in the summer of 1968, after he came back from the Tbilisi meeting. I was not yet in graduate school, but I had the summer to spend, and Wheeler wanted me not to be idle, and so he gave me the problem of the collapse of gravitational waves to form a black hole, incoming gravitational waves focusing to form a black hole. But as he explained to me, and I have it in my PhD thesis, this problem actually is also in his autobiography, which is called Geons, Black Holes, and Quantum Foam. He realized that this was not possible for me to actually solve this problem. So he gave me a simpler model problem, which had spherical symmetry. The original problem has no symmetry. And this was the gravitational collapse of a concentration of scalar field energy. So this with spherical symmetry, I could make some progress. But it took me, even for that problem, quite a number of years to solve. And the actual problem, the general problem, the real one, which namely the focusing of gravitational waves to form a black hole, I solved exactly 40 years after Wheeler gave me this problem in the year 2008. But I could not relate to him that I had found the solution finally, because he had died the month before. And this was very unfortunate, of course, and I felt very moved. So I dedicated that work on the formation of black holes of general relativity, published in 2009, to him. I should, coming back to the Kerr solution, I should say that now it is almost 60 years after its discovery by Roy Kerr, and it still continues to be the crown jewel of general relativity, and it is the focus of the effort by mathematicians, the current effort to prove the stability, finally, in the sense in which Sergio Kleinerman and I proved the stability of the Minkowski spacetime. Now, this is now nearly finished. That is to say, that we nearly have the global nonlinear stability of the Kerr solution for arbitrary value of the angular momentum to squared mass ratio. We are very close to this, and perhaps it will come within the current year. And you will hear more about it in the session of black holes, in particular in the talk by Sergio Kleinerman and also the talk by Michalis Dafermas. Thank you very much again, and it is indeed a great honor. Thank you.
Thank you very much, Dimitrios, for this beautiful perspective and past and future. Of course, the key, since the Lavochkin Institute, Iki, and Rashid, and the people of Max Planck are here, and they launch the most impressive space mission to look the universe as far as possible, one of the key issues is to look for black holes as energy source. And as you remember, the key point from our formula from that point of view was that at least 50, up to 50% of the mass energy of the black hole could be, in principle, extractable. And this is crucial because now we see, like Rashid will show, millions of active galactic nuclei and black holes, and the machine, the inner engine for this, we understand now, comes from the rotational energy of the Kerr black hole. But different from the initial mathematical proof that you are looking for stability, which is of course of paramount importance, is also the possibility that the black hole is not be in vacuum and is in presence of a magnetic field, following a old solution proposed by your teacher Papapetru. And indeed, we can now extract rotational energy from the black hole as a source for gamma ray burst, active galactic nuclei, and ultra-high energy cosmic rays. But this machine, this inner engine, works not with gravity, works with electrodynamics. And there are practically three components: the rotation of the black hole with the gravito-magnetic field, interacting with the magnetic field and generating the dynamical source to accelerate particles. And it needs also, since it's an electrodynamical process, the presence of plasma fully ionized around. A triptych formed by Kerr black hole, a magnetic field, and plasma fully ionized. And we will hear quite a lot during the meeting about this extraction of energy. But let me go back maybe one moment. We have pictures that you can see of that splendid day in Princeton when you at 19 were presenting the thesis. We had a long discussion with Wheeler. Who should we invite to be examiner? And there was no choice. We had the fortune in this day in Princeton to have one of the closest collaborators of Albert Einstein, a marvelous person who was called Eugene Wigner. And in the booklet, if you click, you will see with Einstein for his 70th birthday, Eugene Wigner. Eugene Wigner was one of the kindest person I ever met. He said once, they accused me to be too polite, Wigner. But Wigner was also the person who, in order to have in the scientific dispute, he generalized the word of Niels Bohr. Wheeler told us that in the secretary of Niels Bohr, there was a note for the secretary, and the note said, interesting, equal, wrong. And Eugene generalized, interesting, very interesting, if true. And we all remember him saying that word. As soon as he was pronouncing that word, very interesting, if true, there was the finish of any discussion, and he was going to attack. We were terribly, terribly, terribly afraid that this would happen. And I choose a picture in which he is attacking. And later on, he gave me a dedication. He noticed that among the many questions that if Dimitrios will not answer, I or Wheeler were supposed to answer, he put, for a moment, somebody was in trouble, but then the solution was found. He noticed from my expression that I was concerned. But believe me, there was no need for help from me or from Johnny. He was at the end, he did not pronounce very interesting, if true, but he was finally coming out of a discussion profoundly smiling. This was a tremendous relief and a great joy. Of course, also in that the other professor in the examination was David Wilkinson. And this brings us to space, to the space missions WMAP for looking at the cosmos and the background radiation. And indeed, this brings us to the next topic, because this continuation of WMAP and of looking at the universe and looking at the energetic of black holes bring us back to the Rashid Sunyaev mission, which will be the next topic that we will be presenting the next award. Thank you again, Dimitrios, and let's proceed then with Roy for the next mission.
Okay.
The next award is to Professor Perrin for extending relativistic astrophysics across international frontiers.
No,
yes?
Roy, since we have the possibility, the great possibility to have Steven Weinberg receiving the award, but now is night in Austin. Therefore, we decide to postpone the award of Perrin and Weinberg this afternoon at 2 o'clock chest time, which of course for you will be very late at night. Therefore, now we proceed directly to Rashid Sunyaev and to the institutional award, which goes to Lavochkin, Max Planck, and Space Research. Please go on this award.
Well, the institutional award of the Marcel Grossman Committee will be awarded to the Spectrum for the Spectrum Roentgen Gamma mission. It's for the creation of the world's best X-ray map of the entire sky, for the discovery of millions of previously unknown accreting supermassive black holes at cosmological redshifts, for the detection of X-rays from tens of thousands of galaxy clusters filled mainly with dark matter, and for permitting the detailed investigation of the growth of the large-scale structure of the universe during the era of dark energy dominance. This award goes to the S.A. Lavochkin Association and it will be presented to its designer general, Alexander Shurskov, to the Max Planck Institute for Extraterrestrial Physics, presented to Peter Predel, principal investigator of Rosetta, and to the Space Research Institute of the Russian Academy of Sciences, presented to Professor Rashid Sunyev, principal investigator of the SRG Observatory in Russia.
In this case, we will have not one, but 3 awards, which will go to be located in some of the most prestigious institutes in the world. The Marcel Grossman Award have already been given to the Hubble Space Telescope. If you walk in the entrance of the Hubble Space Telescope Institute, you will find the test sculpture. I hope very much that the same sculpture could be located in the location of the Lavochky Association, and of course to the Max Planck Institute where Rosetta was developed, and especially to the IKI, where all this fantastic history of this satellite started, with Roald Sagdeyev, with the memory and the action and the push and the enthusiasm of Yakov Borisovich Zeldovich, the teacher, the great teacher of Rashid Sunyaev. Therefore, I ask Rashid to go on from this moment on, please.
Maybe we will start with Lavochkin.
Yes. The designer general Alexander Shirshakov. Oh, yes, here we go.
Добрый день, уважаемые коллеги.
Good afternoon, dear colleagues.
Мы выражаем свою признательность оргкомитету и Центру релятивистской астрофизики за высокую оценку нашей работы и присуждение нашему предприятию столь престижной международной премии. Спасибо.
First of all, I would like to express my gratitude to the organizing committee, ICRANET, and International Center for Relativistic Astrophysics for the high assessment of our activities. Is a truly great honor for us to receive such a great award. Thank you.
Мы также выражаем признательность всем нашим партнерам по созданию такой уникальной обсерватории, как спектр РГ.
We also thank our partners who participated in this unique mission aimed at creation of X-ray observatory spectrum RG.
Хотелось бы выразить признательность Институту космических исследований, который участвует в данной церемонии награждения.
We would like to express our special gratitude to the Institute of Space Research, IKI-RAS, who participated in this ceremony with us.
К сожалению, лидера проекта Михаила Павлина нет с нами, но аппарат и телескоп, созданный им, он летает.
Unfortunately, the leader, this scientific leader of this project, Mikhail Pavlinsky, has left us, but the mission he was involved in is successfully launched and operating.
Также хотелось бы выразить чувство глубокой признательности Институту внеземной физики имени Ника.
I would like to express my special thanks to the Institute of Extraterrestrial Physics, named after Max Planck.
И лично господину Питеру Пределю, нашему коллеге и партнеру.
And personally, Mr. Predel, my partner and colleague.
Мы также благодарим все предприятия промышленности, госкорпорации Роскосмос, которые помогли нам создать такой замечательный аппарат.
We also thank all the enterprises, space enterprises incorporated by Roscosmos, who helped us to implement this challenging mission.
Мы выражаем отдельную признательность госкорпорации Роскосмос за всемирную поддержку нашего проекта.
We express our special gratitude to Roscosmos State Corporation for their involvement and their assistance in our joint program, Spectre RG program.
Замруководитель госкорпорации Михаил Хайлов присутствует на данной церемонии.
Mr. Khailov, who is Deputy Director General of Roscosmos State Corporation, is present at our ceremony.
Также я не могу не поблагодарить весь коллектив НПО имени Лавочкина, который собрался здесь на церемонию награждения.
I express my sincere gratitude to the Lavochkin Association team who is present here in our museum.
Невозможно выделить каждого.
Just a moment. Just a moment. We cannot hear. Please, let's wait for. Is the connection with the Lavochkin Association disconnected? Hello? Hello? Is the disconnection? Rashid, are you online?
Yes, I'm online, and I think that Peter is online, but unfortunately, I do not see people from Lavochkin. Something occurred.
Maybe we can go to. Let's wait a moment.
Yes.
And then eventually we can ask EE people to.
Maybe we can ask Peter Predel. He is the next in the line.
Okay, Peter, and then we go to EE, and then we come back to Lavochkin.
Okay.
Okay. Peter, are you ready?
Yes, I'm ready, but shouldn't we wait for another few seconds for Lavochkin?
Yes, absolutely.
Yeah,
absolutely.
if you have the time, I think it would be fair to wait.
Yes, let's wait.
Because there are so many people there.
Yes, absolutely. Let's try to.
A few seconds.
Yes, no problem.
In the meantime, I can thank you. Wish a good morning to everyone. And it's a great honor for me, and I'm very grateful to be part of this ceremony and take the award for the institutional award for the Institute. And I can promise to you, Remo, that it will be in the entrance of our Institute.
Good.
Gregory, are you trying to do something? Is it, or there is completely loss of
We are trying to reach them. Yes, there is a loss at the moment, but let's see if they can respond quickly.
1 second, I will try to call them. Maybe this will help. Да, все ждут вас, вы пропала связь, попытайтесь выйти снова. Хорошо, все ждут. I asked them to try again to contact us, but I don't know.
Yeah, that could take longer, I'm afraid.
I think let's proceed with Peter.
Yeah, that could
And
take
then,
probably long.
and then we give them some.
Colleagues, do you
Yes.
hear us?
Okay, Good.
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 Right.
What do you think? Which moment shall we repeat the speech from Mr. Shirshakov, or you could hear him well?
Oh, when Professor Shishakov mentioned that Deputy Director of Russian Space Agency, Mikhail Khailov, is with us. And
Okay,
Khailov
that was
all of
the
us.
middle of his speech, actually.
Yes, please,
Okay.
because we didn't heard anything else.
Okay, so shall we repeat from that
After,
moment?
No, just go after. What was after
Okay, okay.
this introduction, introducing Mikhail Nikolaevich Khailov?
Михаил Николаевич, после этого нас не слышали, соответственно, можно с той ноты.
Атей, ну я сделал самое главное, я поблагодарил руководство, это уже неплохо.
Well, the most important things were heard by you. Mr. Shishakov had mentioned the top management, so that was the core thing.
Ну а второе, наша космическая связь с космическим аппаратом за 1 700 000 километров, я понял, гораздо надежнее.
And the second thing that he understood currently that the link, the communication with our Spectre RG spacecraft is much more reliable than this telecommunication link.
Я просто не помню перерывов в контактах с нашим аппаратом. Итак, продолжим.
Because there were no pauses in communication with the Spectre RG spacecraft.
Я скажу сейчас самое главное. Мы находимся в музее НПО имени Лавочкина. Я бы хотел, чтобы мы показали всю ту команду, которая создавала, испытывала и управляет космическим аппаратом. Здесь присутствует руководство НПО имени Лаучина в лице генерального директора, а также наши основные специалисты, конструктора, проектанты, руководство проектом. Я думаю, что некоторых из них вы знаете. И та команда, которая сегодня управляет космическим аппаратом. Громадное им всем спасибо.
Now you can see in the screen the whole Lavochkin Association team who were involved in the development of Spectre RG mission. We are currently sitting in our Lavochkin Museum. Here we have our management, our designers, our engineers, test engineers, and spacecraft control team. So almost all core persons who were developed and are currently participating in the operation of the Spectre RG mission.
Сегодня наше предприятие – это современное предприятие, которое продолжает традиции, заложенные еще 80 лет назад по освоению дальнего космоса.
Today, Lavochkin Association is a modern enterprise basing on its huge heritage gained during the almost 80 decades history and proceeding with the development of far space missions.
Мы являемся пионерами в освоении лунной программы, венерианской программы.
We are first explorers in the lunar program, lunar exploration program, Venus exploration program.
Исследование Марса и комет.
We also have some exploration of Mars and comets.
Сегодня мы собрались на территории нашего музея, где вы видите наши достижения, лунные достижения. Это первый искусственный спутник Луны, ну и знаменитый на весь мир луноход.
Now at your screen you have the first moon satellite and the famous lunokhod. They are demonstrated in our museum where currently we are situated.
Сегодняшний НПО имени Лаучина продолжает наши традиции и осваивает новые научные рубежи.
Today, Lavochkin Association, basing on its heritage, going forward in exploring new horizons of the space.
Наиболее известные являются успешно реализованный проект «Радиоастрон», международный проект.
The most famous implemented program is Radioastron program.
Ну и, конечно же, сегодняшняя вершина – это проект «Спектр РГ». Он здесь, макет перед вами.
Of our current exploration is Spectre RG spacecraft. You can see the mock-up in your screen.
Когда-нибудь он займет достойное место в музее, а сейчас пожелаем ему, чтобы он как можно больше и дольше летал и трудился на орбите.
Well, sometime in the future it will certainly take its place in our museum, but for now we would like to wish the mission all the success and long service life in the orbit.
Я хочу пожелать успехов нашей международной команде в управлении обсерватории «Спектр Г».
I would like to wish the best success to our control team, international control team, who is capable of real-time operating of the spacecraft.
Получением все новых и новых научных данных, которыми, я уверен, будем гордиться.
And I would like to wish all our team to have as much interesting and extraordinary scientific data as it could be received from this mission, to explore it and research it for in the future.
Еще раз выражаю признательность за высокую оценку нашего труда. Большое спасибо.
Once again, I would like to express my sincere gratitude for the high assessment of our joint work. Thank you very much.
Thank you very much, Alexander, for this very beautiful presentation, very impressive place and museum. And I am very happy that the test will be located in this incredibly important place, which summarizes the effort of Russia for so many decades and very big success. Thank you again for your beautiful expression. Now we can go to Peter Predel.
Yeah, I started already, but let me repeat my gratitude for being here at this ceremony. Let me tell you a little story about the development of Eurosita. So after the big success we had with the Rosat mission 30 years ago, we always continued with the idea of having another all-sky survey with a better sensitivity and a broader energy range. And then at the turn of the millennium, when cosmology gained a lot of importance, we developed together with colleagues in the US the idea to do cosmology with the X-ray detection of 10,000 clusters of galaxies. And we wrote a proposal within NASA's MAX program, and we fortunately lost, by the way, against New Star. Fortunately, because we realized in the meantime that 10,000 clusters of galaxies wouldn't be by far not sufficient to do a reasonable job. We need 100,000. And in order to cope with this number, 100,000, we had to redesign the instrument, and the number 100,000 became 100,000 galaxies, galaxy clusters became the design driving science for Rosita, and the reason for the E in front of it, E-Rosita. That made the name E-Rosita. And then a year later, or almost as a side effect at that time, we expected also to detect 3 million of supermassive black holes and almost 1 million stars in our own galaxy, apart from all the other objects in the zoo of astronomy. This was a scientific idea and the instrument design. And then we started the very successful cooperation with our ICI colleagues in 2005. And then 15 years later, in 2020, when we finished with the first of 8 all-sky surveys, we saw that our expectations were too conservative, that we can do even better. And now, a year later, and exactly 1 week ago, last Monday, a whole bunch of papers appeared about the first results. And more importantly, we released the first chunk of real E-Rosita data to the world. So everyone can play now with E-Rosita data, with the catalogs, and can make use of our analysis software we have developed at MPE. But the best X-ray telescope is almost useless without a functioning spacecraft. And let me tell how well Lavochkin built it. Alexander Yadumayu Eta Pravilna. Shortly after launch, the spacecraft fell into safe mode. It's always very bad because this happens if something seems to be broken. In this case, a board computer did not receive updated information from the attitude system. So the pointing accuracy of the spacecraft wasn't given. Or better, the board computer believed that there was no update. And as a matter of fact, the spacecraft was and still is so extremely stable. The pointing of the spacecraft is so extremely stable that there was no need to update numbers coming from the attitude control system to the board computer. That tells you, and that is what Alexander told you before, how well this spacecraft was built. Let me come to the other partner, to IKI. And here I would like to mention Michael Pawlinski, sadly posthumously, because he passed away shortly after we finished with the first survey. For 15 years, Michael was the driving force at IKI, and apart from leading the development of his own instrument, Arctic-C, he was the interface between us and Lavochkin. He was supporting and helping and often also pushing us, but always moving things forward all the time. And one shouldn't forget, of course, the support we got from our space agencies, Roscosmos and DLR. And let me come to the Max Planck Institute. You know that in the past, many prizes and awards went to our institute, the Max Planck Institute for Extraterrestrial Physics, but these always went to individuals in the institute. This Marcel Grossman award is, to my knowledge, the first that the MPE receives as an institute. The MPE is honored for the development of an extraordinary instrument, the eROSITA X-ray telescope. And personally, I'm happy and also a little bit proud to have the chance to contribute to this achievement, at least a little bit. And now at the end, I would like to thank Remo and all who have contributed to the decision to award us for our achievement. Thank you very much.
Peter, so happy to have your words and honored to have a test at the Max Planck. As I told you previously, for me, one of the greatest occasion to meet a scientist from Germany was first the meeting I had with Pascual Jordan, and later with Heisenberg, Werner Heisenberg, and how proud he was of the Max Planck institutes that he helped to establish. Therefore, this occasion, I would like to also remember both of them. Thanks. We can go now to the next, to the Space IKI Research Institute on the Russian Academy of Sciences.
Yes, I am representing today IKI, and I was very glad to hear the presentations of Alexander Shishakov and Peter Predel. I will tell now a few words about how everything developed in IKI. IKI is a key scientific institute of the Russian Academy of Sciences, and just today, I was very glad to see here Roy Kerr and Roger Hoft, and to hear Dimitrios and their words about the properties of the black holes. This very deep theory. And I remember also the seminars in Moscow where Zeldovich was present, Ginsburg was leading this seminar also. And during these seminars, people were speaking a lot of the properties of the black holes and theoretical investigation. And majority of people in the hall, and this were maybe 300 people at that time, they were not believing too much. They thought that black holes are just theoretical, they play with mathematics and nothing else. And I am very grateful to people from Lavachkin, people from IKI, people from Max Planck Institute for Extraterrestrial Physics, that they made us, open us the way to see today on the map obtained by SRG, to see the millions of supermassive accreting black holes. And when people, how to say, starting to observe this in detail in different spectral bands, these X-ray detected black holes, supermassive black holes, they discover, for example, we discovered one black hole at redshift 6.18. All spectral atomic lines are shifted in the spectrum of this black hole more than 7 times. And it was, how to say, active when our universe was maybe 15 or 20 times younger than today. And it is very interesting. And, you know, this dream of theorists that black holes will be, that it will be possible to see black holes is now real. And you know that many experiments are looking what is occurring around the event horizon. And I'm very glad that this, our mission, is able to deal with enormous amount of these black holes and to say people which are the most interesting for further investigation. Peter already told about the clusters of galaxies, and we in Moscow were extremely interested in clusters of galaxies. And you know that my mentor Zeldovich and I, we proposed, at that time it was impossible to observe them really in X-rays, clusters of galaxies. Most massive objects in the universe with masses of the order of 10 in power 15 solar masses. And these objects have the most massive gravitationally bound objects in the universe. They filled to 80, more than 80% of mass there is a dark matter. Fritz Zwicky found this many years ago, and now we know that we just all experimental data shows that it's really dark matter. And our dream was to detect this. We proposed how to observe them in using cosmic microwave background radiation. And today I am very glad that eROSITA very successfully competes with Planck spacecraft, well-known cosmological Planck spacecraft, which detected 2,000 clusters in microwave, and then with Atacama Cosmology Telescope, which detected 4,000 clusters on the sky, and with South Pole Telescope, which also has now in their collection more than 5,000 clusters of galaxies. And I can tell you, I can report you that today, eROSITA on SRG is observing of the order of 30,000 clusters of galaxies in X-ray. And when we join this information from microwave band and from X-ray band, we are getting a lot of additional physics, and this huge amount of clusters of galaxies permit us to go further and to see, to check our cosmological models and to look for the, to get much more precise information about many cosmological parameters, and for example, to measure the rest mass of neutrino. I can tell you that our universe, what we see in the universe, we see only finite volume because universe has age and there is horizon, CT. We cannot see much further. Even within this horizon, we have, as Peter already mentioned, only of the order of 100,000 massive clusters of galaxies. And our dream, with the help of these microwave experiments and with the help of eROSITA SRG, to detect all existing today, all visible today in the whole observable universe, all clusters of galaxies, and then to see how they were, how these clusters were formed, how they went, how they were growing, and so on. A lot of information for our observational cosmology. This is great that eROSITA was able to create so great and beautiful map of the sky. I can tell also that a lot of people were working in the whole world on this project. My estimates are that several thousand people were creating our detectors, were working on the grazing incidence mirror, optics mirror for these telescopes, and were producing beautiful space platform navigator, which is working so well carrying our telescopes in space. And I'm grateful very much to people who created Proton rocket, which brought us to the second Lagrangian point of the Sun-Earth system, and distant to this system, to this point, is 1.5 million kilometers from the Earth, 4 times farther than the radius of the Moon orbit. And in this position, Sun, Earth, and Moon are all time from one side of spacecraft. Every day, 2 giant antennae of the Russian Deep Space Network, 164-meter near Moscow in Bear Lakes, and second 70-meter diameter dish near Pacific on the boundary of Russia with North Korea and China. They are working 5 hours per day to dump the data from our spacecraft, to send commands to the telescopes. And this is really, and in a few days, there will be 2 years after our launch. And I can tell you, every day spacecraft was working very well, and scientists are enormously grateful to Lavochkin Association and to other industries of Roscosmos who are working with our observatory. Returning to ET, I am, today we all speaking about Mikhail Pavlinsky because 1st of July last year he left us. And Mikhail now, the telescope for which he was a father, this Arctic Sea telescope, hard X-ray telescope, also grazing incidence. This telescope is also very, very well working on our mission. And it was, I see in the ET room several people who contributed a lot to the success of this telescope and its test and so on. But Misha Pavlinsky obviously was key person, and telescope now is named after him. And he was very good friend and young friend. He came to our group as a student, and you see now we all are proud that there is in the skies 1.5 million kilometers from us, there is a telescope which has name of Mikhail Pavlinsky. I can speak a lot about the science of SRG Observatory, but I can tell you that I hope that there is a lot of scientific news will come from this telescope. And in reality, I should tell you that I am also grateful to scientific community, to the elder scientific community, which at the time in the 60s, 70s, beginning of 80s, when there was no information or very little information about universe and about black holes, we are working on this and we are predicting us the best way to investigate these bodies, predicting the main observational consequences of their existence. Thank you, and many thanks again to thousands of people working in industry, working in scientific institutes, to young students who are working now with data of Spectrum X Observatory. Many, many thanks to all of you and to them for their great contribution to the success of this observatory. And many thanks also to organizing committee of Marcel Grossman meeting, because it is great honor for us to be among institutional organizations which got the prize before us. And Remo already mentioned it, Hubble telescope, great telescope. Chandra X-ray telescope was also got this medal, but also very important that Planck spacecraft team and European Space Agency also got this award. And we are honored to be in this great group of best space organization, scientific spacecraft of the world. Many thanks.
Roy, maybe you have to close the ceremony and be ready to start again at 2 p.m. European time. Excuse me. Yes, to 2 p.m. Time for Tzvi Piran and Steven Weinberg. And I would like to thank you very much, Roy, to have participated in this first part and make the effort to continue later on in the evening. And if we can proceed with the program, Rashid, now going back to the MG program, there is your lecture. You plan to give the lecture now or yes?
I will be glad to give lecture now if whole conference will follow me, because we are here, I see here only maybe together with Lavachkin and Tiki, maybe only 30 or maybe 40 people. But I heard that our conference is in reality more than 1,250 people, and it will be a pleasure to talk for all of them.
Yes.
Rashid, you are seeing just the panelists, but there are many people connected to the meeting, very many.
Very good. And there is also YouTube flow, as I understand, because many people from IKI now are watching this, watching us on YouTube.
Then we can proceed because there are many people who are linked already and they would like to hear your presentation. And therefore, please proceed on the talk, SRG Orbital Observatory X-ray map of the universe with 1 million accreting supermassive black holes. This directed to the large public. We have 1,200 people registered, and many of them are on link. Please, Rashid.
Yes, thank you. Then I will try to continue. Thank you, Marcel Grossman meeting, for invitation, excuse me, to be with you. And I will speak about the best X-ray map of the universe with 1 million accreting black holes. But may I start to show several pictures. What is the SRG Orbital Observatory? First, this is the SRG Orbital Observatory, maybe few weeks before the launch, before it was sent to the Baikonur launch site in Kazakhstan for final tests. You see here navigator platform, which was designed and produced by Lavochkin Association. This is Arctic Sea telescope produced by Russian collaboration led by Space Research Institute and Federal Nuclear Center of Russia. And you see here also eROSITA, and see how giant are these telescopes. Their focal length is huge, and dimensions of eROSITA, for example, and 3.5 meter to 1.9 meter. As Peter should remember, we started our negotiations to bring device from the Max Planck Institute for extraterrestrial physics to our mission, and first proposal from German side, from Günther Heisinger, was device which was also before proposed to Americans, and it was much smaller. But at that time, we also told we need 100,000 clusters, and answer was, but it is enormous weight and enormous power consumption. But our answer was this Russian spacecraft, and it will carry, most important is the science. And then German side designed eROSITA, and you see how huge is it. This proton launcher, and launch was really beautiful. And after launch, our spacecraft was flying 100 days to the L2 point. You see, Earth is here, Moon is here, Sun is very far there, and this is L2 Lagrangian point. And this is our orbit. One revolution around L2 and full sky map we are obtaining every half a year. You see here, oh, excuse me, you see here that this is L2 plane of ecliptic, and you see Earth and Sun. And that axis of the spacecraft is the scan axis, is always directed to the Earth and Sun, and spacecraft is rotating with period 4 hours, and therefore every source on the sky is observed 6 times per day, once during half a year. This permits to look for the variability of the sources. And every day the plane of the scan shifts slowly to 1 degree following the scan and leaving 1 degree wide. You see here 1 degree wide strip on the sky. And when the strips are going, when the scanning is going continuously, we are getting real map of the sky as it's here. I already told that there are 3 great dishes which are working with us, 3 stations of the Russian Deep Space Network who are working with us every day. One is near Moscow, 64-meter antenna, and one near the Ussurisk, which is 70-meter dish, and they're working, and also dishes in Baikonur in Kazakhstan. And all data which are coming practically simultaneously are going to Lavochkin and then to Moscow and to Munich, practically simultaneously. And we are grateful there are in the room several people who are responsible for data receiving and distribution. And I hope that some people on the dishes also are looking our live stream of this presentation. This is Mikhail Pavlinsky Arctic Sea Telescope. You see again, 1st of July, 2020. And this is his telescope, which he designed, and there are 7 crazy coincidences, hard X-ray mirrors. It's very long focal distance and length of the telescope. These are X-ray mirrors. I should mention here, and the detectors which are designed and produced in a key. But about these mirrors, Russia produced its own mirrors, but we compared them with the mirrors from Marshall Space Flight Center, and then NASA permitted to Marshall Space Flight Center to deliver us their mirrors just to get better scientific results. And people from this group is also participating in the data reduction from the Mikhail Pavlinsky Arctic Sea telescope. Yes, this to show you energy. eROSITA is very sensitive from 300 eV up to 2.3 keV. Then, due to the Greisig incidence mirror sensitivity reflection drops, and eROSITA is much less sensitive at the energies higher than 2.3 keV. You see how rapidly it drops. And this is Arctic Sea. It is after 5 keV, Arctic Sea is much more sensitive than eROSITA. And for comparison, this Misha Pavlinsky gave me this picture many years ago. This is the effective surface area of the New Star spacecraft, which was mentioned by Peter Predel. This is the biggest American telescope in hard X-rays, which is working, but which is not scanning sky, but just observing selected objects. Yes, this is map of the central part of our galaxy obtained by Arctic Sea in 412 keV energy band. You see it, a lot of objects. It's very good result. Arctic Sea is really excellent timing machine. For example, you see this is observations of the neutron star rotating with period 150 milliseconds. And time resolution of Arctic Sea is 23 microseconds. And you see this pulsar. This is pulsar nebula filled by relativistic particles. And this is a shock wave when these particles are pressing the interstellar gas. And I am happy that both Alexander Utavinov and Sergei Malkov are following this talk. This is map of the whole sky obtained by Arctic Sea. There are, now I know that there is 850 sources in 412 keV. 60% of them are galactic. You see, these are galactic sources. And these are black holes, neutron stars, white dwarfs, coronally active stars, supernova remnants. And 40% are extragalactic, IGNs, and this is good. The simple sizes reflect the X-ray brightness of the sources. I think that within several years, after additional 2.5 years of sky scan, Arctic Sea will get record, the best in the world map of the universe in this map, in this spectral band. But this is eROSITA, and you see it is not one telescope, but the same is with Arctic Sea, but 7 X-ray telescopes just in the same bunch, and each of them has its own giant X-ray CCD in the focal plane, and each of X-ray mirrors, this is Greisig incidence mirrors, they consist of 54 paraboloids and 54 hyperboloids, each of them. And you see that there is one scattering on parabolic mirror, one scattering on the hyperbolic mirror, and then focus, and you can make X-ray image. One of the best images which eROSITA on SRG got immediately after it was delivered to the L2 to the Halo orbit around L2 point. You see here galactic reach, see, and field 25 square degree. Our resolution, we resolve every object, we see what localize every object with precision 5 arcsecond in this 20 degrees field. Here we see more than 8,000 sources, And I can tell you, these are very different nature of this object. This is the star forming region. And you see here a lot of very young stars, which also are very active and emitting a lot of X-rays. This also very young star T Tauri. It's rather well known. This is very old star, but it has coronae like our sun, and it's nearby, we see it. This pulsar, very rapidly rotating neutron star. We see here supernova remnant. This is death of the star. Another star died, supernova remnant. There are many, many things. I'm telling only about most bright of them. But also, please look to these regions with diffuse emission. This is hot, warm, hot gas, which fills the plane, 80% of the plane of our galaxy. It was predicted by Chris McKee and Jerry Stryker, and we see this hot gas in the plane of the galaxy very well. And where is the cold gas, which we know from 21 centimeter observations, you see that there is strong absorption and we do not see any emission because cold gas just absorbs this soft X-ray emission. Yes, and this is a map, which is just absolutely great map of obtained by SRG Rosita after half a year of flight. Now we have much more data, but here there are 400 million X-ray photons, and you see plane of our galaxy, a lot of black holes in the binary systems here, and these small dots, you see many, many of them, are the extragalactic objects on huge distance from us. And I would not tell you all the objects well known, which is on this sky, Virgo cluster of galaxy, Coma cluster of galaxy, Perseus cluster of galaxy. There is well-known Orion Nebula where young stars, young formed stars we see, Crab Nebula neutron star, a lot of things. And this is the Cygnus region, star forming region, which a lot of supernova remnants, and there is giant radio galaxy Cygnus A. We see X-rays from all of them. It's absolutely great. And this is here the center of our galaxy, our black hole. We also see it, but it is very weak object. And you see also giant regions of the hot gas around center of galaxy. This is the Rosita bubbles, X-ray bubbles, and these are traces of huge explosion in the central part of our galaxy 40 or 60 million years ago. Altogether, there is million of X-ray sources, Milky Way, and these traces of huge explosion. Yes. 3/4 of a million objects on this map are distant quasars and active galactic nuclei powered by accretion of matter onto supermassive black holes residing in their centers. They are very far from the Milky Way at distances of hundreds of billions and billions of light years. We see also 20,000 already in first half a year we saw of scanning. We saw more than 20,000 extended objects, mainly clusters of galaxies and rich, excuse me for mistake, groups of galaxies with hot gas. Yes, great spectroscopy of the Rosita. You see here, during survey, we see, for example, supernova remnant Cygnus loop. 200-second exposition. We see only 200 seconds this object, every pixel, and you see how beautiful is image. And this is a 400 seconds integration during two scans, and you see the spectrum. Hydrogen-like oxygen, this is oxygen nucleus with one electron. L-shell emission from iron. Hydrogen and helium like neon, magnesium, silicon, a lot of lines. Most beautiful maybe is this image. This is the microquasar SS433, and you see two jets moving with velocity 0.26 velocity of light. See, you see here approaching jet, which is coming to us, and receding jet. And there are lines, and again, this is hydrogen like iron, helium like iron, 26 is the charge of nucleus, and only one electron. And this beautiful thing, we study these lines, see, can measure even redshift and blue shift using them. And this is a family of silicon and sulfur lines, which also sees in Rosetta. A lot of people now are very interested in the exoplanets, about the planetary systems around distant stars. And SRG Rosetta, just during first sky survey, detected X-rays from 100 stars with known exoplanets. It's 10% of all nearby stars with known exoplanets were detected during first half a year of the mission. Now, after 3 scans of the whole sky, we have much more. But I think that it's very interesting that we do not see yet in X-rays a single star with exoplanets in habitable zone. And it is good to think that somewhere there is a planet which is not radiated too much. It's also good. Now I told you already how we scan the scan, and now we covered the entire sky 3 times. This is the result. We see the stars of our galaxy with very bright coronae, much brighter than our sun. And this is, we see here a lot of objects. This is differential source counts and X-ray flux. And these are stars, which we are getting, correlating our data with Gaia spacecraft data on stars moving on the sky, nearby stars. Distant objects like supermassive black holes and huge distances do not move at all. Therefore, we immediately separate them, and all these objects are the active galactic nuclei or accreting black holes. It's very interesting. We are scanning, we scanned, we got 3 maps of the whole sky, and we can push one map on another and see are objects variable or not. And typically, we detect 3-5 objects per day, changing their flux more than 10 times during half a year. And you see here, this place in the first scan, there is nothing, no one X-ray photons. These are single photons. We do not see from this region no one single photon. And here you see huge concentration and there is bright object. And this is after half a year. And we think that these are good candidates for tidal star disruption by supermassive black holes. And we detect one good TD candidate every 10 days. Look what is the tidal star disruption. This is supermassive black hole, and star is moving and going rather close to black hole. These are hundreds of gravitational radii. Reinhard Genzel will tell you about star which is moving around supermassive black hole. In our galaxies, this distance there is 2,000 gravitational radii. But if star is going more close to black hole, it is disrupted. Part of matter is going very far from the black hole, and other part is captured, forming accretion disk. This matter falls, and black hole becomes enormously bright. And you see here Eddington limit, and this is the amount of mass accretion up to, it's enormous, 1 solar mass a year it is eating, and you see bright, very, very bright source on the sky. And after 1 year, source disappears. And we are observing, I told you, we're discovering every 10 days, very good candidate for this event. I just show you now objects, X-ray selected, 140,000 X-ray selected quasars, blazars, and AGNs, where we know redshifts. And redshifts are from 0 to redshift 618, which we observe and we know redshifts. And you see here all the majority of luminosities is 1045 ergs per second. You see here 10 power 44, 10 power 43, but some of objects are 10 in power 47 ergs per second. This 10 in power 14 times more than luminosity of our sun. 10 in power 14 times. We see them, and we see them at very, very high redshift, 5, 6, and this is tremendous. Now we are studying in detail these objects. What is the reason of this very high luminosity? Is the gravitational lensing or beaming of the relativistic beams, or what is their nature? These are spectra. We are discovering, we are predicting what should be the redshift of the quasar, and then big telescopes. This is a Russian 6-meter telescope. Observe it several hours and finds, for example, the Lyman alpha line of hydrogen. And everybody knows that the wavelength of Lyman alpha line of hydrogen is 1,260 angstrom. And we see this line near 8,000 angstrom, which just shows us that this object is recessing from us with huge velocity, and redshift is here 5.5. These are young people, and they are especially important. Their contribution is especially important. We already detected during first scan more than 200 objects at redshift higher than 3. And these objects were found with the help of machine learning and neural network programs, which were obtained in the group of Alex Mishirikov. And we continue, to search for the most distant quasars. And when we are telling them that our estimate that redshift is given, then rather small telescope, 1.5 meter telescopes, they're discovering quasars at redshift 4 easily, and success of our prediction is 90%. It's machine learning is great force. Clusters of galaxies, we told already a lot about them with Peter Predel. Our goal is to detect all massive clusters of galaxies in the observable part of the universe. And during our scan, we see a lot of extended objects, tens of thousands. Absolute majority of them are clusters of galaxies. In first survey, for example, number of extended objects with 5 sigma detection was 7,500, with 4 sigma 10,000. 2 surveys gave us 14 or 20,000 clusters only on one hemisphere. It's enormous statistics, and we have what to do. I will show you nearby clusters which we observed with enormous precision. This is Coma cluster of galaxies image of it, and you see here, I just can tell you that there is a logarithmic color code spanning 5 orders of magnitude in brightness. 5 orders of magnitude. And we did this, and there is a lot of distant objects at high redshift and clusters of galaxies in distant regions, but we are very interested in the processes in Coma itself. And look what we are detecting. We are detecting there when we make central part much darker and look for the details there. And we see the, satellite group of galaxies which is moving around cluster of galaxies. So with huge velocity in this huge gravitational potential created by the dark matter and baryonic stars and baryonic matter or hot gas shows us the traces of dark matter. And we see here, you see primary shock, just we see shock, increase of pressure, increase of density. This is secondary shock when matter falls back. We see the bridge between the cluster of galaxy and its satellite, and we see contact discontinuity. This is just a lesson of normal hydrodynamics. We see everything, but characteristic time for this picture, development of this picture, is 1 billion years. You know, people will see practically the same picture after million years if we will survive, if our civilization will survive. There are beautiful data. I can show you also, this is our X-ray image, and this is Planck spacecraft image of the same spacecraft in microwave. You see here, it is due to a Compton-Thomson interaction between CMB and hot gas. And this is negative source in the maps of the Planck, negative, a shadow cast. And here we have positive X-ray emission. And what is important is that just taking ratio of the brightness of microwave to the X-rays, we can measure temperature in any point of the cluster. You see here, for example, temperature is 14 keV, and here of the order of 4 keV, and here only 2 keV. We measure it, and this physics is coming immediately, just comparing the synergy, microwave images and X-ray images. Okay, I think that my time is finishing. Our map is not very uniform. There are, this is north ecliptic pole, south ecliptic pole, all our scans intersect near these poles, and we have huge exposure here. Yes, and this is time just to demonstrate you more than half of the sky. We now have, after 3 surveys, we have time exposure of the order of 800 seconds per pixel. But in the deep survey regions around ecliptic poles, we have exposition of the order of 100 kiloseconds. And this is distribution of the exposition of these our maps. These are survey 1+2. You see again these millions of sources, and this is the third survey. And this uncleared map, we hadn't time to clean it from the solar flare. Its solar flare leaves the traces on our map. We will clean and we will find, nevertheless, we will find what is the image here. Okay, and future plans, additional 2.5 years of scan. We wish to get 8 scans of the whole sky. You will ask me why. First is the variability, second, huge sensitivity, if we will add all these maps together. And map of the Rosat spacecraft, leader was Achim Trumper from MPE. This Rosat produced first very good X-ray map of the whole sky. And people, scientists, were using that maps for 30 years. Our dream to create map which will be serving all scientists for next 20 or 25 years. After that, we plan at least 2 years to work in the Pointing Mount and scan of selected very interesting deep fields. And I told already that we are grateful to many people in Lavachkin, in MPE, in IKI, who are every day sending comments to the spacecraft and telescope, receiving scientific data and sending them to scientists. And many thanks to scientists and engineers who created excellent grazing incidence telescope and navigator platform, proton launcher, to people in the Baikonur launch site for beautiful and successful launch. And many thanks to theorists who predicted for us which effects we should look on the sky and to check the real physical laws of the nature. Many thanks.
Thank you very much, Rashid. Let's see if there are questions. We have to practice a little bit with this method. Dove? If there are questions. Michael Kramer. This.
I think that people are waiting for next talks.
No.
I am also interested in the talk of Michael Kramer.
Cosa? Do it. No. There are people trying to connect.
Okay, so what is the question?
Let's see a moment.
Okay, you can write here your question.
You do?
I have to write?
Yes, right.
Carlos, please, you can ask in voice, please.
Okay. So, okay, thanks a lot for your presentation. Very nice results. Regarding the source, you have shown about the tidal disruption around a supermassive black hole, about reaching 100 solar radii. So, want to know which is the source?
I can tell you that we are preparing paper with, I think that every day amount is changing. I think from 15 to 20 objects were sighted there, and we will announce where they are and so on. It should appear, I think, within a month maximum, because people wish to be very, very careful, and they are also making optical observations. There are on astronomy telegrams, I do not remember exactly the telephone numbers of these objects, but there are in astronomy telegrams, we reported about 2 or 3 cases which were the first. Now it is, like industry, we are getting every 10 days a new object, and it takes a lot of time to process. But we publish every of them, and we informing leading telescopes in the world, for example, Keck telescope, and they're helping us to observe these objects in optical light. And maybe radio or radio telescope, like for example, Meerkat, also will follow some of these objects to see is there radio emission also or not.
Thank you very much, Rashid, again. Then, if there are no other questions, let's proceed to Michael Kramer. New results from testing relativistic gravity with radio pulsars.
Good morning, Rebo. Good morning, everyone. I hope you can hear me. And let me try to share my slides. And as always, it's a pleasure to be here today and to indeed share with you some of the new results that we have obtained in testing relativistic gravity with radio pulsars. Before I do that, let me also express my congratulations to everyone this morning. And if you don't mind, my also particular congratulations to our Max Planck colleagues in Garching. Thank you very much. So let me see. I hope you can see my slides advancing. So before I talk about our tests with radio pulsars, let me remind you that, of course, we do different experiments testing different regimes in gravity. In the solar system, we test the quasi-stationary field, weak field, with pulsars, the S-stars, the black hole images, and so on. We test quasi-stationary strong field regime, but also with pulsars, try to test radiative properties. But if you want to go in the dynamical strong field, then you look at gravitational waves, and we can do this with, of course, ground-based detectors. And soon, I think, also with pulsar timing arrays, which would be another interesting talk given the new results that we all have. And of course, on the longer scales, we have the CMB to look at the universe as a whole, so to speak. But I will talk firmly on pulsars testing the multi-relativistic strong field regime. And the way I want to do that, I give you a very short introduction, but I'll then show you some new results, which I think will demonstrate that we actually have transcended into a new regime with new precisions, new effects. I'll say show some new results on relativistic spin precession, and then try to sort of capture all the other things I cannot talk about, but there are more sessions in that conference that I will refer to. As you all know, of course, pulsars are rotating Newton stars, but they're also cosmic clocks. And whenever they rotate and their beam points in our direction, we can see a pulse. And that comes with the regularity of a good atomic clock. And so we can actually probe the space-time using these clocks as a test mass falling around the common center of mass with a companion. And that allows us to compare this fall with the predictions of your favorite theory of gravity. Of course, this all started with the discovery of the Hulse-Taylor pulsar in 1974, when Russell Hulse and Joe Taylor used the Arecibo telescope to discover that 59 millisecond pulsar that was orbiting an unseen companion in just 8 hours with a highly eccentric orbit, as you can see here from the radial velocity plot. And after a few years, of course, they discovered that the orbit was shrinking, and this is plotted here as a cumulative shift in perihastron time as a function of year. And you know, all this plot, these are the data points, and the red line is the prediction of general relativity. And this is the latest version of it made by Joel Weisberg and his student. And it's really, I think, important to point out the contribution that Joel has had in the exploitation of that system, sometimes sadly overlooked. The system was important because it shows for the first time that gravitational waves do exist. The energy loss is as predicted by general relativity, and the gravity propagates with the speed of light. Also, GR seems to hold for strongly self-gravitating bodies, but of course, we will test that even more in the later slides. And of course, it also showed the existence of double Newton star mergers, which are now being observed by other means, as we all know. So the way we do our tests is we usually use an approach that is called the parameterized post-Keplerian approach, where we basically have theory-independent so-called post-Keplerian parameters that are theory-independent, but each specific theory gives then a prediction of its formula, of its equation that shows how the measured quantity should depend on the Keplerian parameters, as well as the two unknown masses in the system. If you have more than two equations, you can certainly solve for the two masses, and every other post-Keplerian parameters then allows you to do an independent test of your theory of gravity. So for instance, you can plot these curves, these equations into a so-called mass-mass diagram, and if your theory of gravity describes your data correctly, all these lines should intersect in a unique point, which gives you the masses of the system. If the theory fails to do that, and there's no single intersection point, then you should reject the theory as it is falsified. We have done this, of course, with the Hulse-Taylor pulsar. As you can see here, all these, you have three lines that you can plot on this diagram, and the intersection point proves general relativity with a precision of 0.3% in this case. The Hals-Taylor pulsar was for a very long time the best system that we have until we discovered the double pulsar, which is a system of a 23 millisecond pulsar in a 147-minute orbit with another young 2.8 second pulsar, which also was visible. And they have orbital velocities of about 1 million kilometers an hour. What is even more exciting is that we see the orbit actually from this configuration here. So we see it from edge on. So we also have eclipses in the system, which last about 30 seconds, and the orbit is slightly eccentric. And we have discovered a lot of interesting relativistic effects in just a single system. And I'll talk of some of them in the next slides. We have just submitted a couple of weeks ago a complete update of our observations. And most importantly, among those is very precision astrometry, including 2 independent parallax measurements, which gives us the distance to the system. And as you can see here in this diagram, this is the double pulsar, this is the sun. It's much closer to each other than the Hals-Taylor pulsar is to the solar system. So we don't have any unwanted relative acceleration effects to take into account at the moment. Let's talk about some of these orbital parameters and post-Keplerian parameters that we measure. These are the measurements that we've taken. The uncertainty of the last digit is here shown in the brackets. And I just want to point out, for instance, the most precise measured post-Keplerian parameter is the advance of periastron. And indeed, over the last 18 years, we have covered more than 300 degrees of precession of the orbit. And as a result, we can actually measure the orbital precession with a precision that is 35 times larger than smaller than the second post-Newtonian contribution, which will be important if you want to measure the moment of inertia, as I will show you in the following. Overall, these results are based on 1 million times of arrival measurements, which give us an excellent cadence. And that is, for instance, also demonstrated nicely when we look at the gravitational wave emission. We can see that the orbit is also shrinking due to the emission of gravitational waves. And we have measured that with a precision in the exchange over a period of 7 picoseconds a day. And this is the beautiful parabola plot that we get for the double pulsar. It demonstrates both the excellent cadence that we have, and the red line is the prediction of general relativity. And it also shows how well the theory matches the observations. It's just beautiful, like pearl on the string. And indeed, expressed in numbers, the ratio between the expected and observed value compared to general relativity is in excellent agreement, validating GR in this case at a level of 1.3 times 10 to the minus 4 with 95% confidence limit. In fact, our precision is so high that for the first time we have to take the mass loss due to rotational spin down into account. As the pulsar spins down, it loses rotational energy, and E is equal to mc squared, as we all know. And so the pulsar loses 8.5 million tons of mass every second. That seems to be a lot, but actually it's only 3.2 times 10 to the minus 21 of its own mass. But still, we have to take this into account because it makes about a third of our error budget right now. We also see light propagation in strong gravitational fields, which is difficult in most experiments. We can use this to measure the inclination angle of the orbit, which is very close to 90 degrees. And that means that the signal of the background pulsar has to pass the foreground pulsar in only 10,600 kilometer distance. And so as the photons have to propagate through this curved space-time, it takes slightly longer than in flat space-time. And that leads to a delay of about 130 microseconds. Again, here, the red curve is our prediction from general relativity, and the blue data points are our measurements. From the shape, the amplitude of the curve, we get 2 tests of general relativity, and again, it's passed with flying colors. Actually, if you look very, very carefully and zoom into this green box here, which I'll show you on the next slide, then you actually find that in the normal lowest order Shapiro delay description, you actually see some deviations. And the deviations are shown here. When I subtract the red curve from these blue data points, we get this signature here. That signature is very systematic. The pulse arrives increasingly late at later phases, and then it's a peer conjunction, it swaps signs, and then the pulse arrives a little early. That is the result of 2 combined effects. Both of them are from the next leading order in the Shapiro delay. One is simply retardation, and we have discovered that the speed of light is finite, which basically means that the photon, as it is emitted from pulsar A, by the time it arrives on the other side of the orbit of pulsar B has moved slightly, and that has an effect of the measured Shapiro delay curve, and that's a 1.5 pn contribution to the Shapiro delay. However, there's more. This effect alone doesn't explain it. What you also need to take into account is light bending. As the space-time around the companion pulsar is curved, the photon from pulsar A has to be emitted under a certain angle to compensate that bending in the space-time around B, and in order to reach our observer near at Earth in distance. So in order, before superior conjunction, you have to emit the pulse a little late, the photon a little late compared to the normal rotation. That's why the pulse comes increasingly late. And then immediately after superior conjunction, the pulsar has to shoot the photons in the opposite direction to compensate in the other way. And that's why you have the signature going in the opposite way. And that actually gives you very nicely the spin direction of the pulsar in an independent way. So, and you will find it's prograde with the orbital angular momentum vector. And this extra bending adds the 600 kilometers to the 10,600 that you get from a purely geometrical orbital configuration. So that's why we have 10,000 kilometers from just the orbital inclination and 600 kilometers from the light bending. And if you try to measure the effect, you'll find it is also in good agreement with general relativity's prediction. And I just want to point out, without going into much detail in this complex diagram, we really, with pulsar experiments, we can probe photon propagation in the largest space-time curvatures, which are orders of magnitude larger than what, for instance, you can do with images of black holes or in a solar system. And so these tests are very valuable because there are almost no other experiment, or there's no other experiment that can actually do that. One curious fact that we also see is the relativistic deformation of the orbit. It's a consequence of the equation of motion in curved space-time. The orbit is actually not fully elliptical, but it is kind of like deformed. This is exaggerated here in this plot. It looks more like an egg shape. And we have measured this effect, not to very high precision, but if you wouldn't take this into account, you would actually see an apparent disagreement of GR in the Einstein post-Keplerian parameters gamma, but actually in reality, everything is perfectly consistent with the prediction of GR. Let me talk about lens steering. We have, of course, measured, as I mentioned, the precession of the orbit to extremely high precision. And at that level, we actually have to take lens steering contributions into account. So frame dragging actually contributes a contribution to the observed or precession of periastron. And the idea is now, if we can separate the second post-Newtonian contribution from the lens steering contribution, we can have actually access to the moment of inertia of the Newton star just based on pulsar timing alone. And we have done this, and we are not quite there yet. We need more precision, but we clearly see that the contribution is non-zero. And we can, by marginalizing over all reasonable equations of state, we get very precise mesh measurements. And we also have a first non-zero measurement of the moment of inertia, which is consistent with other measurements. And we can also put an upper limit on the Newton star just based on pulsar timing of 22 kilometers and 9% confidence limits. That isn't great yet, but we have better observations coming up. And I'll refer to Wan Chen's talk in the session on Wednesday morning, where she will talk more about our current measurements, which will actually lead to a firm measurement of this effect. Finally, putting everything together for the double pulsar, 18 years of the discovery. This is the mass diagram for this source. It has many, many more lines than the Hals-Taylor pulsar, as we have measured 7 post-Keplerian parameters plus this theory-independent mass ratio. We provide the most precise strong field test of GR, and here is a summary of the tests that we are doing. This is, again, the ratio of the observed to the expected value in GR. We have shown you that we start to probe the moment of inertia, and hence the equation of state of the Newton star with pulsar timing, and that we need to take the mass loss, the rotational mass loss, into account. Again, with Meerkat, Rashid also mentioned the telescope already, we can actually improve our timing precision by a factor of 2 to 3, and Wan Chen will talk about some of these new observations, as I said, on Wednesday morning. Let me say a few words about relativistic spin precession. That is, of course, a geodetic precession observed in the solar system with experiments like lunar laser ranging or LARIS or gravity probe B. But in strong field, there was Thibault Damour and Remo Ruffini who pointed out immediately after the discovery of the Hals-Taylor pulsar that we should also see this in that particular object. And indeed, it took us some time to actually confirm the effect, but here is a plot of the pulse width as a function of time, which is clearly showing the effect of spin precession, which changes our line of sight as it moves through the emission cone as a function of time. This was a qualitative confirmation. It took us some time to actually make a significant measurement of the precession rate to compare it with general relativity. And that was done somewhat later with a double pulsar, again, where we have used these eclipses that I mentioned in passing to make that measurement. The point is that the magnetosphere of the slow pulsar blocks the light of the background pulsar and produces this beautiful eclipse pattern that you can see here emerging on the screen. And as the pulsar moves in the background and blocks and unblocks, blocks and unblocks the light, you get a very significant distinct pattern which changes as the spin axis precesses in space. And so you monitor this eclipse pattern as a function of time, and that led René Breton in his thesis at the time to validation of GR's prediction at a 13% level. And I'll show you how we're going to improve on this. We have MICAD observations ongoing, and so Huan Chen is dealing with the timing of the double pulsar, and Markus Lohr from Swinburne University, he is looking at the eclipse pattern, and this is sort of the GBT observations that we had. And here you see this beautiful pattern that we observe with MICAD. The data quality is truly awesome. And even after some very short number of observations, Markus is already getting some preliminary numbers which confirm the René Breton et al. And the result, and we believe we can improve the precision by maybe up to a factor of 10 even. So stay tuned for that result. Another beautiful result that we about spin precession, geodetic precession, that we published last 2 years ago by now. Here we use a pulsar where we have, which is a young pulsar in a relativistic orbit. It's also a double Newton star system. And we see actually used to see the two north and the south pole of the pulsar as the orientation is almost orthogonal to us as an observer. And here we use the idea of that we also look at the rotating vector model, which means the position angle swing as a function of pulse phase. And this is a model proposed by Randa Krishna Cook already in 1969, was never really confirmed in earnest. But it says that the position angle swing, the angle of the polarized radio emission has this distinct S-like shape as we cross the pole. And this is due to the fact that we measure the polarization angle as the projection of the field line direction onto our line of sight. The closer you are to the pole, the steeper that curve is. And even if you're on the other side of the pole, you will expect the opposite S-like swing, which is in fact consistent with our observations. Now we monitor this pulsar also for more than 10 years. And in this very nice work that we published in 2019, we basically were able to track the line of sight of the south pole of this pulsar as it crosses the magnetic pole for the first time and goes on further. And this is exactly what you can see here. The curve becomes steeper and steeper as we get closer to the magnetic pole, and then suddenly it flips and has the opposite direction. So this not only confirms the famous Randa Krishna Cook model very nicely, but it also allows us to do a very precise measurement of the precession rate, which is again in very good agreement with GR's prediction. And the other thing we can do about it is, of course, we can measure the beam shape in the latitudinal direction very nicely. And that allows us actually to work also an improved Newton star merger rate for gravitational wave detectors, as we usually don't have that latitudinal information. Let me change the topic for the last couple of minutes of my talk. There's so much more we can do with radio pulsars, and I just don't have the time to go through all of them. So I just give you a quick summary of everything else, not everything else, a lot of other things we can do with pulsars testing relativistic gravity. And one of the things I want to highlight is that we can test the universality of free fall. So we can test the weak equivalence principle very nicely in the solar system. For instance, beautiful results from the microscope satellite. We can also test it with lunar laser ranging, where we can use the moon and the Earth system to see how they fall in the gravitational field of the sun. But if you want to take a pulsar and the white dwarf system, you can do this even in strong fields. And here the most beautiful example is that of the triple system, where we have an orbit between a pulsar and a white dwarf and an outer white dwarf around it. And that led Archibald and colleagues to provide this very stringent constraint on the Nordwest strong field equivalent in that system. We have recently actually published an update on that system. We used a different data set taken with a Nancy telescope, a very high cadence, very high quality, and also having a more consistent way of analyzing the data by incorporating the possible strong field variations of the strong equivalence principle right in a timing model. We get an even better constraint on the Nordwest parameter here written down as a Taylor expansion of the gravitational binding energy. And that limit is not only more stringent, but also derived in a more self-consistent way. We can also look at the universality of free fall towards dark matter, and I just refer to this paper if you want to see this for details. I won't have time to go into it, but we can also sort of use an already very well-studied pulsar white dwarf system to put some constraints towards dark matter behavior. And if you had such a system actually in the galactic center, you can do even much, much better, because we expect much higher dark matter concentration over there. But I refer to this paper for more details. And there's so many other things I could talk about that are completely different talks. Therefore, let me just refer to Paulo Freire's talk on Wednesday morning as well, in the same session where Huan Chen is talking. He will mention new limits on existence of gravitational dipole radiation or variation of the gravitational constant. And there are some other papers that you may want to consult, graviton mass bounds or test of conversation laws, or just have a look at some recent reviews that you find in literature if you want to really study the details. Let me just finalize with one last example, testing parametric theories. Here, as an example, because it's very well developed, we can test, for instance, the Moore-Esposito-Farese gravity, which is a two-parameter monoscalar tensor gravity. Here, you basically have a diagram where you have your parameters of the theory in such a plot. Everything below a certain line given by a given experiment is forbidden. Everything below the line is allowed, and GR would lie here at minus infinity on this axis here, which is also the Barnes-Dickey theory. And for instance, if you pick a theory that lies here and compute the mass diagram for the double pulsar, you'll see what I said at the beginning. These lines don't intersect, and therefore this particular theory here, the star, should be rejected. You can see actually the best line is given by the triple system here, which is basically given much better constraints for almost all the parameter space, apart from a small fraction here where Cassini still gives a better limit, and here where the double pulsar cuts off at least two negative betas. But have a look at this paper. It's a beautiful work, and I think that just shows you the other kind of things you can do with binary pulsars. Let me summarize. I think it's really sad that Einstein did not live to see the discovery of pulsars and their usage to test relativistic gravity. Despite all the other beautiful experiments that we have these days with other results and complementary, binary pulsars still provide the most precise and often most unique test for strongly self-gravitating bodies. The advantage that we have usually clean and precise measurements, because we deal with test masses, and all of them confirm GR so far. As I indicated in the last couple of slides, we also have tight constraints on alternative theories, which all have to pass binary pulsar tests. But really, we should combine all the binary pulsar tests with other results from other experiments to combine and get the best results that are possible. I think I demonstrated to you that we have made significant progress with the double pulsar and the triple system, but in particular with the double pulsar, we have transcended into the next level of precision. And even as we do this, more systems are discovered, which may also promise to be such excellent contributions. And again, I refer you to the Wednesday session if you want to learn more. And finally, with MeerKAT, as already mentioned, but also the FAST telescope in China and later SKA, we really have the chance to do even much, much more and basically combine with the things we have done today. So there's much, much more to come. Finally, my very, very last slide, let me conclude with my famous quote, my favorite quote, not my famous, of Albert Einstein in a letter to Arnold Sommerfeld in December 1915, shortly after he presented his field equations, commenting on the fact that he could verify his field equations as first time with the perihelion measurements of Mercury. And he says, there comes the pedantic precision of astronomy to the rescue, which I have ridiculed silently so often in the past. And if he really liked the Mercury perihelion precision, I hope he would also have liked our pulsar precision. Thank you very much, everyone.
Thank you so much for this splendid talk, showing how incredible the precision of verification of validity of general relativity has reached. You have given a fantastic redundancy with binary, triple system, and even finding this verification of that prediction with the move inspired by the GPB experiment. But you do that not only increasing the technology on the ground, but increasing the observation of the verification of these phenomena in the universe. Where do we go from here?
Well, we discover more systems. We have discovered a number of new double Newton systems, which are also highly relativistic just in the last couple of years. And we are making new discoveries. Just like yesterday, we discovered a new pulsar with MeerKAT, which looks very promising. So I think there will be more systems, but more importantly, with these new telescopes, we can also increase the timing precision even further. And so that will allow us to really push it to the next limit, which means we have to do a little bit more work in order to be clean about possible systematics and measurement uncertainties and so on. But that's the fun in it. So I've never thought we have to take the mass loss of a pulsar into account when it rotates, but it happens. So yes.
Yes, this of the mass loss is really incredibly, fantastic. But well, just congratulate you.
Thank you very much. Much appreciated.
If there is any intervention. I don't know if people are aware of this chat.
So I have a question. So I'm Valerio Bozza, and I'm curious about the gravitational lensing of the double pulsar. So you have been able to measure the gravitational bending of the pulse during the passage of the pulsar on the background of the foreground pulsar. But are you also able to see the secondary image from gravitational lensing? So the negative parity image of the pulse?
It's actually not lensing as such. It's actually more aberrational light bending. It's not the gravitational lensing. For the lensing itself, to see kind of an Einstein ring, for instance, you actually have to be even closer to 90 degrees. So what we really see is a contribution from an aberrational light bending across the pulsar. So it's not quite, so we haven't quite seen a lensing image, but for that, the orbit needs to be even more inclined as it is. But we clearly see the signature of the light bending, of the aberrational light bending in our data.
Okay, thanks.
Hello. I have a question regarding another effect that may affect the times of arrival, namely the propagation between the propagation effects between the pulsar system and the observer through the galaxy. What kind of effects do you have to take into account in?
Can you identify yourself?
Mikołaj Korzyński from Warsaw.
Oh, good.
Hi, Mikołaj. Yeah, good question. We usually would have to take into account any change in the propagation in between. So there could be interstellar medium effects, which we can take into account by observing a different frequency. So if you have multiple frequency, then you can actually calibrate your data to calculate, to determine any frequency dependent delay due to interstellar medium. There could be relative acceleration between the solar system and your pulsar. And that's what we worry about most. That's the reason why the Hals-Taylor pulsar is not improved over all these years, because the relative acceleration can only be measured with a certain precision, which limits the test in the Hals-Taylor pulsar. Fortunately for the double pulsar, there are actually two contributions: the relative acceleration in the gravitational potential and the so-called Shklovsky effect, which is the secular acceleration. For the gravitational potential, we are very lucky that's actually very close by. And for the Shklovsky effect, we can actually do the parallax measurement. We can determine that value now very precisely. In fact, both of these effects cancel each other to some extent. And so very lucky that the overall contribution is small anyway, but we can also take care of this right now with the precise distance measurements. Otherwise, everything else should be more or less fixed between, as long as nothing changes, then this is just a constant offset to the arrival times that we can't measure. So we basically have an uncalibrated offset that corresponds to the propagation time as such. Does that answer your question?
Yes, thank you very much.
You're welcome.
Let's see. Who is? Okay. Okay. You have a question?
Yes, good morning. It's Jorge Rueda from ICRANET. Yes, I have a question because dark matter also modified the dynamics of binary. So my question is, are you planning, or what do you need, or when you estimate that it will be possible to measure the effects of dark matter on the dynamics of the binary system?
We can already put some very stringent limits on that. You talk about dark matter. Did I hear this, Roger, correctly? Dark matter or matter? Yeah. So yes, here I would really I'd like to refer you to a paper that we wrote with Li Shao, which looks exactly at the kind of question you point out. So the dark matter would actually modify the orbit, and we can pick this up with, for instance, a change in eccentricity of the system with time. And by dealing with this in an appropriate way, we can put already a limit on the interaction with dark matter. But that limit would be orders of magnitude better if you find it if you've had such a system in an area of the galaxy where the dark matter content is supposed to be high, for instance, near the galactic center. So it would be very nice to have such a precise system over there. And you can look at the plots in that paper how we deal with this. But you can already put some limits on existing systems as we have it right now.
Oh, that's nice. Thank you. Thank you.
Welcome.
Okay. Okay. Another question?
Yeah, just a comment on the previous question. So there's some work, also works by Diego Blas and others on the change of orbital period caused on some binary pulsars, especially those close, as Michael was saying, closer to the galactic center. And Diana Lopez Nasir and other people have been looking at that precisely what you're saying, at the ways in which the interaction with dark matter might modify the dynamics of binary pulsars. Yeah.
Yeah, thanks, Paolo. That's a good comment. Thank you.
Okay. Well, if not, let's thank again Michael for this splendid talk. And let's keep waiting for the new instrument.
Yes.
And see how many of these objects of profound interest can be found inside the galaxy and outside even. And we look forward also to the Chinese participation on this. And we will have a plenary talk on Thursday by the director of that instrument. Okay, again, thank you very much.
Thank you very much, Simon. Thank you.
I proceed already the Marcel Postman Award years ago. We are very happy you continue in this great tradition. Thanks.
Thank you very much.
Let's go to the next talk by Miller Jones. Are you there?
Yes, can you hear me?
Good. Yes, we can see you, finally. After reading so much about you, but we can see you in person now.
Okay.
Well, this is a long story since the early days of the Uhuru telescope and the very, very exciting time in which we identify Cygnus X1. And I still remember a fantastic meeting in New York, chaired by John Wheeler, and the first time that we proposed this identification of Cygnus X1, not without some objection, but now the situation is becoming even more accurate. And we look very, very much forward to your talk to see the technology which has allowed to bet this much deeper precise mass estimate, which makes the system Cygnus X1 even more interesting than the initial prediction of tensor mass. Please.
Thank you very much. So thank you to you and to the organizers for inviting me to talk about these exciting results. It was very nice to see this identified as one of the prominent X-ray sources in Rashid's beautiful eRosita maps that he showed us a few minutes ago. And I'll also pick up on the theme of precision astrometry that Michael identified. I can't compete with a number of decimal places, but I'll certainly show what can be done with very high precision astrometry in this case, picking out motions to just a few nanoradians. So this is work that was done by a large group of collaborators here, the main contributors listed on slide. I'd particularly like to call out the work of two students, Kuhn Neissel, who worked on the implications of our work for the evolution of the system, and also Suishan Zhao, who did a lot of the work on fitting the black hole spin that I will tell you about. Okay, so I think many of you will have seen plots somewhat like this coming out from LIGO and Virgo in terms of a comparison of the gravitational wave black hole masses shown in blue with the black hole masses measured in X-ray binary systems from electromagnetic observations, and those are shown in purple with all the neutron stars down at the bottom in yellow. And you'll see that by and large, the electromagnetically detected black holes, which come from X-ray binaries in our own galaxy or nearby galaxies, are typically significantly less massive than the ones found by LIGO. They span a range of maybe 4 to perhaps 20 solar masses, whereas the LIGO black holes, the progenitors at least, are between about 7 and about 50 solar masses. So to date, the two most massive claimed black holes that we know of electromagnetically are both seen as ultraluminous X-ray sources in external galaxies. So they're in Wolf-Rayet systems where a massive Wolf-Rayet star is losing a lot of mass via its stellar winds, which is being accreted by a compact object. So here are the two galaxies, IC10X1 on the left and NGC 300 on the right. And the X-ray sources in here are suggested to have had masses of 20 solar masses or a little bit above. They're measured via radial velocity measurements in the optical. So we look at the radial velocities of the donor star as it moves around its orbit with its unseen companion. And those variations can be used to infer the black hole mass. The trouble with these Wolf-Rayet systems, however, is that these radial velocities are measured from the emission lines, which could well be coming from the wind. And so that leads to some slight uncertainty in the actual masses that are derived. Beyond those two, the most massive two black holes that we have known about are M33X7, which is the one shown on the right of the screen over here, and then Cygnus X1, which is circled in red with its previous best estimate of the mass of about 15 solar masses for the black hole. So our work uses VLBI astrometry to refine the distance to that object, which has a large impact on our inferred mass and makes it the most massive electromagnetically detected black hole known to date, and poses some challenges to the theories of how such black holes can form. So the final mass of a black hole is set by the mass of its progenitor star, affected by the mass lost in winds and binary encounters over the course of its evolution, plus any accretion and mergers that it has undergone during its lifetime. So here's a plot from Chris Belcinci's paper from about a decade ago, showing the maximum remnant mass, so the maximum black hole mass that can be formed for a given set of progenitor masses, these zero-age main sequence masses that are shown on the x-axis. So you'll see that depending on the metallicity of the environment, whether it's solar metallicity as seen at the top, 0.3 times the solar metallicity, or 1% of solar as appropriate for globular clusters, the black hole masses vary quite considerably. But in all cases, there is a maximum mass that can be reached. And this is very much affected by the wind mass loss rates from the progenitor star, in particular by the Wolf-Rayet winds and the luminous blue variable wind. So these are two phases of stellar evolution after the main sequence that cause a lot of these, the mass to be lost. So those winds kick in at different points according to the metallicity of the progenitor star. So at higher metallicities, the Wolf-Rayet winds are thought to be stronger. And depending on the metallicity, they kick in at different progenitor mass regimes. The main point to take away is that Cygnus X1 is formed, is in a galactic environment at probably roughly solar, maybe very slightly subsolar metallicity. And so the theoretical predictions from the wind models are that the maximum black hole mass that should be formed in such an environment is of order 15 solar masses, according to these wind prescriptions from Vink et al. They're slightly different from some previous predictions by Jared Hurley and his collaborators in dialing down the luminous blue variable wind strength, but increasing the wind strength as a function of metallicity during the Wolf-Rayet phase and reducing the Wolf-Rayet wind clumping. So according to the properties of the wind, that's going to set the maximum black hole mass that we can form in a given environment. So just as a quick recap of where these phases of stellar evolution are, here's a Hertzsprung-Russell diagram with effective temperature on the bottom axis, increasing to the left, and luminosity on the y-axis. And you can see this black track down the center is the main sequence, and stars of given masses will follow these evolutionary tracks shown in red. So stars that are too massive won't be able to get to a red supergiant phase. Instead, they'll pass through a luminous blue variable phase where the atmosphere is loosely bound and the star is fairly unstable and a lot of mass is lost. And then all of these stars will move into a Wolf-Rayet phase where you have a bare helium star with very strong winds before they ultimately end their lives in a supernova. So these are the phases that we're concerned about in terms of the wind mass loss. Okay, so having set the scene there, obviously we'll talk a little bit about the target. So Cygnus X1, as Raymond mentioned, was first discovered back in the 60s via suborbital rocket flights. And so here you see the original X-ray detection of this X-ray source from the Cygnus region. That was subsequently located with radio observations in the early 1970s. And here's a preliminary radio spectrum from Gelming and Wade. And that allowed the association, it provided an accurate position that allowed the association with a massive O-type star. And the radial velocity variations of that O star as it went around its orbit with an unseen compact object allowed the first inferences that this hosted a massive compact object that looked as though it could well be a black hole. So here is a plot of the predicted masses of the permitted masses of the two objects, the visible donor star and the unseen compact object here. And then this stippled region was the best guess as to the parameters of the system here. So you'll see the best guess is an inclination of a few tens, maybe up to about 30 degrees or thereabouts, with a donor star of 25, 30 solar masses and a black hole of maybe 15 solar masses or thereabouts. So this is the first confirmed black hole. It's got a mass function of about 0.25 solar masses, which with information about the mass of the donor star and the inclination angle can be used to determine the black hole mass. So we know now that this is a high mass X-ray binary system. The donor star is an O-type supergiant that's very close to filling its Roche lobe. The orbital period is about 5.5 days. And the black hole is accreting via a focused wind from the donor. So you see here a schematic of the density of the wind shown in the color scale here. And you see the donor star in this classical teardrop shape due to the distortion as it almost fills its Roche lobe. So we know very well the mass loss rate from the donor star. It's about a few times 10 to the -6 solar masses per year. And that gives us accretion, which produces the X-ray emission that we observe and gives rise to the radio emission from the jets, as you can see in this artist's impression. Now, the distance estimates for this system have been figured out from a number of possible lines of evidence, from photometry to H-gamma line widths, extinction maps, the distance of the nearby Cygnus OB3 association, and so on. And so the best estimates of the distance fell in this range, about 1.8 to 2.5 kiloparsecs. Now, the inferred black hole mass depends very heavily on the distance. We can see the donor star, we can measure its flux. So if we know the distance, we can get its luminosity, and hence from the temperature, we can infer the radius of the donor star. And then that's an important parameter in figuring out its mass, and hence from the dynamical model of the system, the mass of the black hole. So as the distance varies, the inferred black hole mass will also vary. These two columns are for different Roche lobe filling factors. Either the system completely fills its Roche lobe on the right or almost fills its Roche lobe, 90% on the left here. So the best guess distance range from many studies over the past few decades is in this range here, which would suggest a black hole mass somewhere in the range of 11 to 35 solar masses or thereabouts. So the best method for measuring distances is via geometric parallax. So just a quick reminder of what that is. If we measure the position of the source from opposite sides of the Earth's orbit, we can use simple trigonometry to figure out how far away the system is. So this has traditionally been done with VLBI in the radio band, but also more recently using the Gaia satellite, which has provided billions of astrometric measurements and precise distances to many, many sources. So the best existing distance constraint was from a VLBI, set of VLBI measurements by Mark Reed and his collaborators from about 10 years ago. And so you see here in the left-hand panel, this is the motion of Cygnus X1 across the sky relative to two different calibrators. That shows you the red and the blue traces that they're for the different calibrator sources that were used. And you can see both a linear motion as the source moves across the sky due to its proper motion, and an annual wobble that gives the curvature here due to the parallax. So Mark and his collaborators made 5 different measurements, very nicely sampling the opposite sides of the parallax curve to provide the best possible constraints on the distance. So the middle panel here shows the motion in right ascension on the top and in declination on the bottom. And then subtracting off the proper motion, you can see the parallax curves here in both right ascension and declination. And so these are very well sampled, and they provided a very precise measurement of the parallax to the source. And that parallax was about 0.53 milliarc seconds. In fact, those measurements also detected the orbital motion of the black hole. So the VLBA is picking up the radio emission from the jets, which are launched from close to the black hole. And so the jets should be tracking the motion of the black hole as it moves around its orbit. Equipped with an accurate distance, we can then determine from the flux that we receive in the optical what the luminosity of the star is. And with that luminosity, as I said, we can get, and a measurement of the effective temperature, we can get at the stellar radius, which is a key input to the dynamical models that seek to model both the photometric variations of the system and the radial velocity variations as the donor star moves around its 5.6-day orbit. So what we see as the star moves around its orbit, we see that the projected area of the donor star changes. So when the star is seen side on, we see the full teardrop shape, which is a larger area than we would see if we're observing the star face on. And so that causes these intensity variations just due to the AET to the fourth, the area factor in the luminosity equation. And that's correlated with the radial velocity variations as it moves around its orbit. So by modeling these photometric variations in the brightness of the donor star and also the radial velocity, we can figure out key properties of the system, both the mass ratio and also the inclination angle of the system. If the system is seen completely face on, we will see no changes in the projected area, whereas if it's seen edge on, that will give us the maximum changes. And so from the magnitude of these variations, we can work out the properties of the system and hence the component masses. So using that previous VLBI distance that Jerry Arosh and his collaborators fitted both the photometric light curves in the optical band and also the radial velocity curves to figure out a donor mass of about 19 solar masses and a black hole mass of about 15 solar masses. So here's a schematic of what the system looks like from their work. So we have the orbit here, the black hole at inferior conjunction when it's closest to us, and here's the O-star supergiant. And that gave a very good picture of the system. Now, because the supergiant is almost filling its Roche lobe, the geometry is very well constrained. The size of the Roche lobe is set by the mean density of the star. So that fixes the ratio m over r cubed. Since luminosity goes as distance squared and goes as radius squared, then the radius is proportional to the distance, meaning that the mass inferred for the donor scales as distance to the third power. So the masses that we infer are actually very, very sensitive to the distance, which is another reason why we need a high precision distance measurement for the source. Now, as I said, the Gaia satellite has recently measured some very, very accurate astrometric positions for sources and determined the parallax to nearby bright sources such as Cygnus X1. And there was a bit of a tension between the original Gaia DR2 results, so second data release, and the radio results. And that was only compounded by the early data release, EDR3, for Gaia in December last year. So here you see in black the probability density function for the distance from the VLBI measurements, and in blue and red, the Gaia DR2 and DR3 values. So you can see there was a bit of a disagreement between the radio and the optical values. And it was unclear what was causing that. Could this be a global offset in the 0 point for Gaia? Could it be an effect of the radio wobble from the black hole orbit and the optical wobble from the donor star orbit? It wasn't clear quite what was going on. Another issue with the previous measurements was that at the inferred distance, the inferred mass of the donor star violated the mass-luminosity relationship for core hydrogen-burning stars. So you can see two different mass-luminosity relationships here depending on different stellar wind prescriptions. So this is the mass and luminosity, and the position inferred from that previous work was right over here, so well off the expected relationships. So we made some new VLBA observations a few years ago where we observed the system for 6 consecutive days, so tracking it around a full binary orbit. And we minimized the astrometric systematics by finding a much closer calibrator source. Typically, the systematic errors vary with the distance between the astrometric target and the calibrator sources. So by finding a closer calibrator source, we were able to reduce the size of the systematic errors affecting our measurements. And what we saw in our data was an orbital modulation in the measured positions of the source. So what I'm showing you here in the right-hand panel, you see our best fitting orbit as the ellipse in the center. And you see the measured positions at different phases of the orbit over here. Now the red points are our new measurements, and the blue points are the previous measurements from Reed et al. And the dashed lines track them back to their positions on the orbit. And what you see is that there's a significant scatter up and down the jet axis. So here's an image of the radio jet, and we're tracking the core of this jet and measuring its position very precisely to get these positions, which are tracking the motion of the black hole. I note that this is on a scale of 10 to the 7, 10 to the 8 gravitational radii, so it's quite a long way downstream. But nonetheless, what we're seeing is that when the black hole is closest to us, so on the near side of its orbit, all the positions are scattered downstream towards the binary system, whereas when it's on the far side of its orbit, so it's on the opposite side of the donor star from us, all the positions are scattered upstream along the jet axis. So this is likely to be biasing our measurements of the parallax to the source. You can see that the old measurements used to determine the parallax, several of them are taken at superior conjunction to the black hole, and this one at inferior conjunction, and that could distort the parallax measurement. Now, it's been known for a long time that the radio emission from this system is modulated on the orbital period, and that's what you see on the right-hand panel here. And that modulation varies as a function of frequency. So at 8.4 gigahertz, which is where we observed with the VLBA, that modulation is about 14% or so. And what's thought to be happening here is that the black hole is moving through the stellar wind of the companion. That stellar wind is quite dense, and free absorption in that stellar wind attenuates the radio emission. So when it's on the far side of its orbit, there's more attenuation due to this free absorption. What that means is that when the black hole is closest to us, it's traveling through least stellar wind. So the radio photosphere, where the jets become optically thin, and we can see them, is a little bit closer to the black hole. Whereas when the black hole is on the far side of its orbit at superior conjunction, the radio emission has to travel a longer path through that free absorbing wind. So the photosphere is pushed out downstream along the jets, and we're seeing it displaced along the jet axis. So we think that that is what is causing this orbital phase dependence of the distance up and down the jet axis that we measured in our astrometry. So in order to take account of this effect, rather than doing a standard two-dimensional fit to the positions of the source to determine the parallax and the orbital size and the proper motion, instead, we only fit in the dimension perpendicular to the jet axis, which is well established and stable on the plane of the sky. So that allowed us to refine our fits to the data. So you can see here the standard two-dimensional fit in both right ascension and declination. You can see the error bars are significantly smaller than would be required for good agreement with the best fitting model. So this is having subtracted out the proper motion and the parallax and the orbital motion of the source. If we only fit in one dimension instead, just perpendicular to the jet axis, we see these error bars instead, which provide a much better fit and reduce the parallax to a level that is now much more consistent with the Gaia measurement. So we can be fairly confident that we're doing the right thing. So as I showed you before, we can compare the Gaia values, EDR3 in red, with the radio values shown in black, and they agree much better than they did before. And also there's very good agreements of the proper motions in both right ascension and in declination. The uncertainties have gone up a little bit because we're fitting only in one dimension, but we get a much more accurate measurement. So that reduced parallax gives us a slightly larger distance than we'd measured in the past. And so that meant that we had to refit the orbital modulations, the photometry and the radial velocities in order to determine the component masses and the various other parameters of the system. So Jerry Arosh led a lot of this work. And so fitting for 9 parameters, the inclination, eccentricity, argument of periastron, donor star mass, Roche lobe fitting factor, effective temperature, semi-amplitude of the radial velocity curve, ephemeris errors, and the rotational velocity of the star relative to the orbital frequency. And those all gave very nice Gaussian error bars. And we got a revised donor mass that was much higher than had been seen before, so about 40 solar masses. And significantly, the black hole mass had risen to 21.2 solar masses. So here's the distribution of inferred black hole masses. So this is significantly higher than we'd measured in the past. We also measured the size of the orbits and the radio orbital size measured directly from the astrometry agreed very well with what we got out from the optical modeling, which gives us more confidence in the results. And you can see that parallel to the jet axis, the black hole position, or the radio position, is scattered upstream away from the black hole when the black hole's on the far side of the orbit to us, and downstream close to the black hole when it's on the near side, as expected. This new measurement for the mass of the donor and its luminosity agrees much better with the mass-luminosity relationship that I showed you before. That varies a little bit depending on the assumed composition of the donor star, which is still not 100% clear, but this is the old value in cyan and new value in blue, and you can see we have much better agreement. So that's also solved that problem. So with a refined distance, mass, and inclination angle, we can try to get a better handle on the spin of the black hole as well. So for a spinning black hole, the spin of the black hole will determine the position of the innermost stable circular orbit, assuming that within that there is no emission. So you can see the predicted dependence of the ISCO as a function of black hole spin in gravitational radii over here. And you can see a fit to the soft X-ray spectrum from the disk that allows, and a proper general relativistic fit to that spectrum allows us to determine the black hole spin, where the major uncertainties come from the black hole mass, distance, and inclination angle, which we've now refined with our new measurements. So what we found by putting these new measurements in is that the black hole spin is still, as was previously measured, close to maximum spin. In fact, it's slightly above the Thorne limit, probably due to the assumptions going into the model, things like a razor-thin disk and so on. Either way, the black hole is very highly spinning, and that is independent of small uncertainties in either the inclination angle, the mass, or the distance to the system. So it's certainly a very rapidly spinning black hole. Now we know this is a high mass X-ray binary system, so it's fairly young, maybe only a few million years old. So it cannot have been spun up by accretion over its lifetime. We also know that there was very little natal kick for the system, and it has a fairly low eccentricity. So it's unlikely that that high spin was created when the black hole was formed. And therefore that spin must reflect the angular momentum of the core of the progenitor star, which tells us something about how we think the system may have formed. So as I mentioned before, the proper motion of Cygnus X1 shows that it received very little natal kick when it was formed. So here's some beautiful work by Felix Mirabel, who I think is going to talk immediately afterwards, showing the proper motion of Cygnus X1 across the sky relative to Cygnus OB3, which is thought to be the stellar association in which Cygnus X1 formed. And they share a common proper motion, which suggests that this got very, very little natal kick. There was very little mass ejection when the black hole formed. The jets are consistent with being aligned with the orbit. We know the orientation of the jets on the plane of the sky, and by measuring the orbit with our astrometry, we can say that the two appear to be consistent. It's got a very low eccentricity. There are no X-ray quasi-periodic oscillations that might be the sign of precession. And so it's likely that the black hole formed with maybe complete fallback, or maybe only a very small amount, less than a solar mass of ejection. So taking all this into account and trying to explain how we could have such a rapidly spinning black hole created and at such a high mass, we considered how, a possible scenario by which this could have formed. So one way to get a rapidly spinning black hole would be to have mass transfer from the black hole progenitor while it was on the main sequence. So we remove enough material to prevent re-expansion after the main sequence phase. During this mass transfer, the system remained tightly locked, and so the core of the black hole, or the progenitor, would end up rapidly spinning. Then it would collapse down to a helium main sequence star. Wolf-Rayet wind mass loss in that phase would widen the binary, and then subsequently it would collapse into a black hole with minimal mass loss. So this spin up via K-same mass transfer on the main sequence could create this rapidly spinning black hole. So as far as the future evolution of the system is concerned, it's about the donor star is currently about 80% of the way through its main sequence lifetime. It'll eventually overflow its Roche lobe and appear as a super Eddington source. accounting for the helium being synthesized in the donor before it's stripped and the reduced Wolf-Rayet wind mass loss that we infer from our measurements, we think this is likely to become a binary black hole, but it is unlikely to merge within a Hubble time. So there's about a 62% chance of the binary remaining bound after the supernova. So just depending on the direction and magnitude of the supernova kick, and only a few % chance that it will merge within a Hubble time. Now, one of the most important ramifications of these new measurements of this black hole mass is that we formed a 21 solar mass black hole at roughly solar metallicity. Now, given that I showed you at the beginning that the predicted maximum remnant mass is a function of metallicity and depends on the stellar wind strength, and was about 15 solar masses for solar metallicity under the Vinkedal wind prescriptions. In order to form something that's 21 solar masses, we have to reduce the strength of those stellar winds, particularly during either the luminous blue variable phase or the Wolf-Rayet phase of evolution. Now, the strength of these winds are typically parameterized by these factors out at the front, FLBV and FWR, which give us the strength, the relative strength of those winds. And so looking at the strength of those winds and the maximum remnant mass that could be produced at a metallicity of about 0.02, this is the default assumptions, which could give us a maximum mass of about 15 solar masses. Here, this is the median mass of Cygnus X1, and the dashed lines show us the 1 sigma error bars. And so in order to reproduce the observed mass, we'd have to reduce the luminous blue variable winds by a factor of about 1/3, or the Wolf-Rayet winds by a factor of about 3. So these reduced winds would allow us to produce higher mass black holes at all metallicities, allowing us to produce gravitational wave sources at intermediate rather than just very low metallicities, enabling a shorter time delay between the formation and the merger. However, this is unlikely to be, Cygnus X1 is unlikely to lead to a binary black hole, the typical systems that are being observed by LIGO and Virgo. Most of those systems seem to have low or misaligned spins, whereas Cygnus X1 has a very high spin that's well aligned with the orbital plane. So most LIGO Virgo black holes seem to go through a different formation pathway. The reduced stellar winds would also give less enrichment of the interstellar medium, and mean that more massive stars at moderate metallicity could retain some hydrogen, which would change the observational signatures of some supernovae. So I think that's a quick rundown of our results and their implications. So we now think that Cygnus X1, this first black hole ever confirmed, now contains a black hole that's about 21 solar masses. And to form that, we have to modify our existing prescriptions for stellar wind mass loss rates in massive stars. We've refined the distance to the source and resolved some of the discrepancies that had arisen from the previous measurements. And we've got a proposed formation pathway and likely future evolution for the system. So I'll leave it there. Thank you very much.
Well, thank you so much for this fascinating and beautiful talk, showing how much progress has been done. When we were working on binary X-ray sources with Ricardo, we had pointed out the difference between the other binary X-ray sources and Cygnus X1, because the other one were pulsating, while this one was just short-time variability. Then both of them were emitting a large amount of X-ray, but the fundamental difference for qualifying Cygnus X1 as black hole was that the mass was larger than the absolute over limit of the neutron star critical mass. Otherwise, there could be a same system, but could not be a neutron star because the mass was much larger than the absolute upper limit on the critical mass. But now we have added, you have added fantastic new information, especially the fact of the spin, the magnetic field. All these present a new problematic. And while a regular binary like SNX3, we had made a mistake not to understand that they could evolve in a short time and therefore give up origin to the gamma ray burst. In this case, the time of evolution you're speaking about, this new possible binary, is more the Hubble time. This creates an additional, very interesting situation. I thank you so much, and let's see, I'm sure that there will be questions to be asked.
Yes, I have a question, Felix Mirabel.
Felix, yes, you have not only a question, but you will have a talk after. Yes.
Okay, but may I ask the question?
Absolutely.
Yes. Yes. Well, as you mentioned, the masses of black holes being estimated by LIGO Virgo are systematically larger than the masses of the black holes in X-ray binaries. And in your talk, you mentioned that there was an effect due to the interaction with the wind of the companion star. And that I believe, if I understood well, you make a correction of the effect of the absorption of the wind from the donor star. Could this be a systematic effect also in all high mass black hole X-ray binaries?
So the reason that that the wind had a big effect was on the astrometry. So it affected our measured positions and therefore compromised or biased the distance measurement to the system. I'm not aware, but you may be able to correct me, of other high mass black hole X-ray binaries with a precise parallax distance that could be affected in this way. I mean, some of the other systems, LMCX1, LMCX3, I think they're too far away to have good parallax measurements for them, certainly in the radio. And so I don't think that those systems could be affected. Now, in principle, absolutely, this is an effect that should be accounted for when measuring parallaxes to high mass systems in which the jets could be affected by this free absorption. But I don't know of any other systems, and maybe you can correct me, that this could influence with current capabilities at least.
Okay, thank you. Thank you very much. Nice talk.
Thank you.
Work.
Let's see if there are other questions. Well, if not, let's thank you again for this very, very impressive talk. Thank you so much.
Thank you.
Let's go to the next stop. Ready to go, Felix?
Yes.
Back in Europe from Argentina, and you look in good shape. And let's look over your lecture.
I try to join my. Yeah. Do you see my screen? Can you see my screen?
In the 21 centimeter line of H1 at cosmos.
Oh, okay. 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 I don't know how to get rid of this. Okay. Well, I should mention that I became interested in the subject of this talk after a talk by Rashid Sonayev at the 7th microquasar workshop that took place in Turkey in 2008, where Rashid talked about the impact of microquasars on the interstellar medium of galaxies. And since at that time I had the idea or the hypothesis that systems of black hole high mass X-ray binaries should be prolifically formed in the early epochs of the evolution of the universe, I became interested to see what could be the impact of microquasars in the intergalactic medium during the epoch of reionization. And so with Luis Felipe Rodriguez, my colleague and friend, we started to work during this pandemic on what will be the imprint of black holes in the 21 centimeter line of atomic hydrogen at cosmic dawn. Cosmic dawn is a relatively short transition phase that lasted about 30 million years between the so-called dark ages and the epoch of reionization, that is a very complex process that lasted for about 1 billion years. And one of the natural questions that we ask is whether what were the nature of the first galaxies and stars formed during cosmic dawn that was produced by the first massive stars formed in the universe. Well, observationally, the most distant galaxy detected so far, according to my understanding, is a galaxy at a redshift of 11. And there are now about more than 200 quasars discovered at redshifts greater than 6 up to redshifts of 7.5 that are hosting supermassive black holes of 10 to the 8, 10 to the 9 solar masses, which is a puzzle how these black holes could have grown from stars so rapidly to reach these observed masses. Now, stars and black holes are not detected, of population 3 are not detected directly, but it has been proposed that these objects could be imprinted in the 21 centimeter line of atomic hydrogen. And here I'm showing a plot of a model, theoretical model, where in the y-axis is shown the brightness temperature of the 21 centimeter line of atomic hydrogen as a function of frequency. And the thing we did in this publication with Avi Loeb and his postdocs at that time in 2011 was to see how will affect the injection of X-rays from X-ray binaries, the large number of black hole X-ray binaries that should exist at that epoch. And this absorption is due to the coupling of the spin temperature of atomic hydrogen with the Lyman alpha radiation of population 3 stars. And there have been many models about this theoretically expected absorption line. What I want to stress is that the amplitude of the absorption against the cosmic microwave background depends on the injection of X-rays into the intergalactic medium where the cold atomic hydrogen is located. So with increasing X-rays, the peak amplitude of the absorption decreases because the X-rays hit the intergalactic gas, and also the frequency decreases, so goes to very low frequencies. So the detection of this absorption line is one of the main motivations of several radio astronomy projects for low frequencies, because it will be the way to get an indirect hint of what was the nature of the first stars and black holes formed in the universe. And these projects can be divided into classes: interferometers, with which one can make fluctuation measurements and get rid of the variations of the foreground emission. And the most powerful instruments to try to detect this absorption line is the SKA. Another cheaper and faster approach are experiments to detect the global signal from the highly redshifted atomic hydrogen, like edges that consist in receivers with a single polarization. Now, 3 years ago, in Nature was published the first tentative detection of an absorption line. What we have done is to put in the same diagram the brightness temperature as a function of redshifts and the age of the universe, in color, the predicted absorptions against the cosmic microwave background, and the edges absorption, which produce great surprise, great excitement, and motivated very interesting research. Now, the big surprise was that that this additional amplitude of the absorption that was not previously predicted. Second, the bottom flat absorption here, instead of being Gaussian shape as had been predicted, and since this signal is about 3 orders of magnitude below the sky foreground, there have been concerns on the analysis of the edges data by the edges team. And this controversy obviously needs assessment by independent observations. We, with Luis Felipe Rodriguez, we do not judge on the cosmic origin of the edges absorption. We don't say if it is real, if it is of cosmic origin or a consequence of systematics in the observing system. And we don't intend to make a new model because there have been many models already of the edges reported absorption. We simply provide approximate calculations to analyze the onset of this absorption, namely this deep absorption between redshifts of about 20 and 18. And with the aim to study in the future this type of absorption signals, taking edges as an example, and explore what could be learned from future observations like this one reported by edges. Now, there have been two families of explanations of this edges absorption. One are models based on new physics, where the absorption is due to cooling mechanisms of the atomic hydrogen by agents like dark matter, neutrinos, cosmic strings. And the other family of models are based on astrophysical mechanisms. First, mechanisms like non-previously accounted effects of the Lyman alpha background. And the other alternative is that besides the cosmic microwave background, could exist a cosmic radio background that boosts the atomic hydrogen absorption. And a first interpretation of this was, or proposal was by this cosmic radio background being produced at redshift greater than 20 by very energetic supernovae of very massive stars of thousands of masses, solar masses. And the most popular interpretation in the context of astrophysical mechanism is the possibility of a cosmic radio background produced by black holes formed very early in the universe at redshifts greater than 18. Now, soon after the publication of this edges report, there was in Astrophysical Letters a publication where, under the title Astrophysical Radio Backgrounds Cannot Explain Edges. And although this is valid for extended radio lobes, the author of this paper didn't take into account the compact, highly magnetized compact jets of black holes. And while using the same equations in that publication, we showed that because the magnetic field, for instance, in sinus X1, we calculated that it must be at least a few tenths of Gauss, at least, is a very low limit. And in AGNs, the magnetic fields must be larger than 100 to 10,000 Gauss, depending on the source, which implies that the synchrotron emission of this type of jets using the same equation of this author will dominate the inverse Compton produced by interaction with the cosmic microwave background by several orders of magnitudes of 10 to the 4 for stellar mass black hole at least, and 10 to the 9 for supermassive black hole compact jets. So this obstacle for a cosmic review background has been removed by our calculations. Now, the idea I had in 2011, and this was published with Adi Loeb and his postdocs, is that black hole high mass X-ray binaries should be prolifically produced at cosmic dawn. And here you see the Cygnus X1 in large scales, is here Cygnus X1, and here is the compact jet by James that he showed. You see that points in the same direction where at 5 parsecs is seen a large bow shock. So this compact jet here is capable to produce at distances of several parsecs these bow shocks. Integral has shown that besides the Comptonized emission of in Cygnus X1, there is also a power law beyond emission at energies larger than 400 kiloelectron volts up to 2 megaelectron volts. And this power law, according to my colleagues of Saclay, is polarized by about 76%, which will imply enormous magnetic fields of greater than 10 to the 4 in these compact jets. So most of the accretion power, when one compares the radioluminosity of Cygnus X1 with the X-ray luminosity, one realized that is 7 orders of magnitude below the radioluminosity, below the X-ray luminosity. However, these jets produce these bow shocks, and the power of the jets must be very large. So, sorry, I don't know how to get rid of this. So most of the, sorry. So most of the energy being accreted by the black hole is converted into mechanical energy that produces radiatively inefficient massive outflows that are mildly relativistic. So we have derived an equation that to evaluate, to calculate the number of radio sources that will be required to match the onset of the edge's absorption depending on observables. This is the flux density of the that correspond to the edge's amplitude at the onset of the absorption. This is the luminosity of the source frequency interval, and this is the flux density at present, and DL is the luminosity distance. So for any type of radio source, we can estimate what should be the number of that type of sources necessary to match edges, this very large amplitude. So applying this equation to what we know about Cygnus X1, it is found that it will be required a few times 10 to the 20 sources like Cygnus X1 to match the edges onset of absorption. And this is a very large number. And from this, we conclude that the cosmic radio background required to match the onset of the edges signal cannot be provided by black hole high massive Troy binaries at cosmic dawn unless they are radically different from known black hole high massive Troy binaries in the local universe, because they will over the masses of these required of these black hole high mass X-ray binaries should be in between 6 and 7 orders of magnitude larger than the theoretically expected mass in stars at redshifts of 19. And also this number of sources like Cygnus X1 at redshift of 19 will overproduce the cosmic X-ray background by 3 orders of magnitude. So the question is, what other types of sources could match edges? And here you see we have a look at sources like the Crab Nebula, ultraluminous infrared galaxies like ARC-220, and we find that all sources of radio sources could not explain this large amplitude except quasars as P172, and this quasar is the most radioluminous quasar found so far at a redshift of 6.8, and we use this quasar as the prototype of rapidly mass-growing radioluminous massive black holes during cosmic dawn. And assuming that the radioluminosity of these massive black holes during cosmic dawn scale linearly with the mass, we find that in black holes there should be about, in masses, about a fraction of 50% of the mass in stars during black holes. So the quantity of mass of the mass in black holes should be enormous, so half the mass in stars. So under the hypothesis of a black hole cosmic radio background, and assuming a black hole mass ratio luminosity as in the quasar P172, the onset of the edge signal requires that 50% of the total stellar mass at cosmic dawn be invested already in black holes. This total black hole mass over the stellar mass ratio is about 14 times larger than the black hole to stellar mass ratio estimated in the Milky Way. Now, these massive black holes grow embedded in hydrogen densities larger than 10 to the 24 per square centimeter. This is a result from observations with the Wide Field Infrared Survey Explorer called WISE and ALMA. ALMA has shown that the majority of quasars at redshifts greater than 6 reside in ultraluminous infrared galaxies. And here you see the observations of quasars at about a redshift of 6 in the carbon-2 158 microns, and the emission in this line implied that the star formation rate densities in the galaxy hosts of this massive black hole, growing massive black holes, are in between 100 and 1,000 solar masses per year per square kiloparsec, as is found in ultraluminous infrared galaxies in the local universe like ARC-220, where the column density along the line of sight to the central sources in this prototype of Euler is greater than 10 to the 24 per square centimeter. And these enormous column densities of hydrogen block the potentially heating soft X-rays, block the access of these X-rays into the cold intergalactic medium on large distant scales. However, the 21 centimeter line emission, for the 21 centimeter line emission, these column densities are transparent for the radio waves. So one can have sources of X-rays where the X-rays and radio waves, where the X-rays remain blocked close to the source and do not access into the cold absorbing atomic hydrogen in the intergalactic medium. And these column densities also are a necessary condition for super Eddington mass growth of black holes at cosmic dawn, which helps to understand how black holes with masses of 10 to the 9 solar masses could have been built at redshifts of 7.5. So I don't have time to go into the timing of the H1 absorption. Perhaps it can be asked, and also I cannot go into the detail of what can be expected with SKA, but I would like to go into the summary. First, among all possible sources of a cosmic radio background, radioluminous massive black holes are the sources that can match the edges onset of H1 absorption at cosmic dawn. The with our calculations, we have demonstrated that the two possible main obstacles to a black hole cosmic radio background at cosmic dawn can be now removed, and the onset of the edges throw cannot be matched by black hole high mass X-ray binaries as observed today, because of reasons that we have been working during this perspective article. They are inefficient radio sources. So they produce essentially turbulence and bow shocks in the environment, but not radio waves. To match the steep onset of the edges absorption in the interval of redshifts between 20 and 18, the total mass in black holes should be about 50% of the expected overall stellar mass formed at those early cosmic times. And this implies that the stellar and black hole initial mass function was at those epochs very top-heavy. Concerning the possibilities with SKA, we estimate that only black holes with masses larger than 10 million solar masses, or those black holes with blazar geometry, will be detected individually with SKA at cosmic dawn. But alternative groups of tens of galaxies, each with a radio loud central black holes, will provide detectable signal. Well, thank you very much.
Thank you, Felix, very much. Let's see if there are questions. It's a new approach, and I think will be very stimulating to look for confirmation of these very, very big black holes of 10 to the 8, 10 to the 9 solar masses, born from small mass black hole relatively, but in very quick time. By the way, I was curious, you mentioned a limit, a field of 10 to the 4th Gauss in the jet in Cygnus X1. Did I understand correctly?
Yes, this is the minimum. The minimum magnetic field could be larger. So, but it's a minimum, is what we are certain.
But let me tell you, this would be extremely interesting, because from the mechanism that we are looking for generation, the E over M purported in the previous talk for Cygnus X1 is very close to 1. Therefore, there could be a very interesting interaction between the gravito-magnetic field of the black hole and that magnetic field generating very strong electrodynamics. And we are working on that, but I did not realize before that how interesting this process is before hearing your talk. Thank you. There are maybe other questions. Carl?
Yes. Hello, Felix. Thank you for the presentation. Well, I have a couple of observations from CONICET Argentina and ICRANET. And I have a question on this peculiar, one of the most recent observation of the quasar P172 plus 18 that was detected at redshift about 7. So you make this strong statement that starting from a population of 3 stars of order 10 to 2 solar masses, you could build an intermediate massive black holes of 10 to 3 to then grow to this 10 to 8 supermassive black hole from redshift around 20 up to redshift 7. So the question is, do you have these physical processes and the reference about these quite, which are still, I believe, very specific physics to make this to happen? If you could mention this paper or references, Felix?
Yes. Well, yes. There was very early this model by Begelman, where he, by a physical mechanism of photon trapping in these large column densities, the black hole could increase its mass super Eddington, in a way of super Eddington, and this is something that in the community that is trying to account for the existence of this 10 to the 9 solar mass, 10 to the 9 solar masses black holes at redshift of 7. There are now many models that try to account for it. One possibility is to start with seeds that are massive, seeds of 1,000 solar masses, but actually with Luis Felipe Rodriguez, we made the calculations, and just starting with a black hole, a seed of 85 solar masses, or in between 50 and 100 solar masses at a redshift of 30, just with Eddington accretion, one can account for this black hole P of 10 to the, some units of 10 to the 8 solar masses.
Okay.
So there should be some periods of super Eddington accretion, but I mean mean Eddington accretion is just enough to account for these black holes.
Thank you so much again. I think we have to move forward to the next public lecture by Mirzoyan. Razmik, are you online?
Yes, I'm online, yeah. Hello, Rama.
Don't worry, you will have all your time because we care very much to hear from you as much as possible. Therefore, don't worry about time. Go on and give this public lecture. Thanks.
Thank you very much. Felix, I would like to ask you if you can stop sharing the screen. Otherwise, I could not enter.
Razmik, we see you.
Yes, I know that you see me, but I think Felix is still sharing his slides. He should stop sharing that I can share my slides.
Gregory.
Thank you. Yes, usually host is doing this.
Okay.
So you can see my slides?
We see you.
No, we do not see your slides yet. Okay, thank you very much. First of all, I would like to thank the organizers for inviting to this very representative meeting. And today we heard wonderful presentations about the X-ray sky black holes, pulsars, microquasars. And after all this, I want to offer you some glimpses about a branch of the science where we are looking to the highest energy gamma rays.
Razmik, excuse me, we still don't see your slides. Can you try the sharing again, please?
You cannot see my slides. Should I share again?
Yes.
Please share your slides. I am sharing. Okay.
Oh, now we see it.
Okay, sorry. I don't know what was. Now you can see it, right?
Yes.
Okay, good. So today I will be talking about the highest energy gamma rays in the universe and some special type of instruments, so-called Cherenkov imaging telescopes, which are measuring these gamma rays. So my idea will be to give you some glimpses about what we are doing. So as usual for productive instruments, it is difficult to go to too many results and bombard the audience with diversity of results. So I have selected several results, and then I will feel very happy if I could give you an impression that I could explain you what we are doing, how we are doing, and what are the results. So I think I start with the telemagic atmospheric gamma ray imaging Cherenkov telescope. I would like to start with it because I'm working with it since the very first days of its construction. So this is an array of two telescopes, and telescopes have a diameter of 17 meters. They stand on 85 meters from each other on the Canary island of La Palma at Roque de los Muchachos Northern Observatory. In the background, you see on the left, you see, for example, the famous Wilhelm Herschel 4.5 meter telescope, Nordic optical telescope, 2.5 meter diameter. Grand Tecan telescope is located there. So, okay, so I will not enter into technical stuff. The location height is 2,200 meters, and then this is a good height for Cherenkov telescopes. So I show you a picture which was chosen by Astronomy Picture of the Day last year. And then this shows our telescope during observation in night. And you can see the Magic 1 telescope on the right. In the center, you see the Magic 2 telescope. And on the left, you can see the first large-sized telescope of CTA collaboration, the 23-meter diameter telescope. Also, you can see a comet here, which you may remember from last year. So we go forward. Our telescope has an angular resolution typically of 0.05 degrees to 0.1 degree. And the energy resolution for us is between 15 to 20%. And then sensitivity range is between 20 GeV to 100 tera electron volts. This is Magic 1, Magic 2, 23 meter diameter LST, and Comet Neowise. So we are about 200 astrophysicists from 12 countries, mostly of European origin, but also several countries outside of Europe show strong participation. It is, for example, Japan, has a strong team. But the main contributors in this experiment are Germany, Italy, Spain, with number of institutions, but also you can see institutions from Switzerland, Bulgaria, Armenia, Finland, Croatia, and India. So there are three major instruments in our discipline. This is the Veritas instrument in Arizona, 4 times 12 meter diameter telescopes. Then the next major instrument is HESS, which is located in Namibia, 4 times 12 meter diameter telescopes, and gigantic 28 meter telescope in the middle. And these are the two magics that I just said a few words about it. So I will start talking about some relatively recent results. For example, last year we were happy to discover emission of Geminga pulsar in the energy range above 15 GeV, between 15 to 75 GeV. So this is the third official pulsar known at very high energies. And it was not so straightforward that there was a gamma ray emission from this old pulsar, which has an age of about 340,000 years. But because it is not on a large distance from us, a modest distance of something like maybe 200, 250 parsec, in 80 hours of data, we could measure some significant signal from the source, which is shown to your attention here. On the left, you can see the artist's impression, how this is looking like, and the realistic measurement from NASA, and then below that, artist's impression is shown here. So why this was important, or just to say a few words, and here you can see the spectrum from the Fermi satellite mission from Fermi-Lat and from MAGIC merged together. And then this is very, very useful when we combine the data, because in a very wide energy range, we can make fits to this data. So what is remarkable, we can see a very steep power law, something like minus 5.1 for this source. And then, in fact, we were anticipating a cutoff in the spectrum of this source. But then instead of cutoff, we see a strong hint that this is continuing as a power law. So sub-exponential cutoff and exponential cutoffs were disfavored to some level. So I think we are thinking again that we are dealing with power law spectrum at highest energies. And why this is important, I will tell you in one slide later on. Yeah? And then we asked our theory colleagues to look into this data and to adjust the model. But the existing models are experiencing difficulties yet to describe emission of Geminga pulsar. I think this Geminga pulsar is a very interesting source, because those of you who are at least as old as myself may remember Haleakala instrument from the beginning of 1990s who were trying to measure signal from Geminga. There were claims more than 30 years ago about gamma ray emission from the source, but it was very elusive until very recently. So I will not enter into details of models because it may be a little bit complex, like contribution from the heated polar cap model. But I want to say that now theory people are looking into this data and trying to see how better one can fit this result. So I mentioned that I would like to show you another result. This is the spectrum of crab pulsar measured at energies about several tens of GeV until 2 tera electron volt. This is a measurement by MAGIC telescope. And it was a very big surprise that the pulsar can emit pulses until 2 tera electron volt. This result has been measured 4 years ago, and it was even a larger surprise that the spectrum continues as a straight line in this log-log scale. And then straight line in log-log scale speaks about the power law. And the power law is an indication that there is a inverse component emission mechanisms at work here. Because any estimate of synchrotron emission shows that it can go until maybe a few GeV, but not higher. So I think then now you can see the similarity between this crab pulsar, and then I was talking about Geminga pulsar, and then we are curious to see if this is an exception or this is a rule for pulsars, that the higher energy end is typically emitted via inverse component emission mechanism. Just a short note, I think there are strong indications that the gamma ray emission is coming from the close neighborhood of the light cylinder. And then this makes them very, very compact accelerators, the most compact accelerators of particles, because, for example, in the case of crab pulsar, the light cylinder radius is 1,600 kilometers. So this is a cartoon about extensive air showers, how we measure them, and then we measure them from the zenith or close to the zenith, and then there is air shower which extends maybe 10 kilometers long, and then the distance from the center of air shower, which is shower marked to the telescope, is also roughly 10 kilometers. But when we go to large zenith angles, I think the distance can become 100, 150 kilometers. What makes the difference from small zenith angles, a chunk of light is illuminating just a spot of 300-meter diameter around the telescope. But if you go to large zenith angle of, let's say, 70, 80 degrees, this becomes 10 times large. So then, keeping this idea in mind, I show you, for example, a photo from the Roque de los Muchachos about the sunset. So we see with our eyes the sunset, just before the sunset. So the zenith angle is short before 90 degrees, marginally short before. But we see it with our eyes, which means light is arriving to us. This tells us also some part of Cherenkov light should arrive. On the left-hand side, you can see measurement of the spectrum of Zeta Tauri, which is a star from the Crab Nebula. You can see there is a lot of light arriving to us for wavelengths about 500 nanometers. So by using this technique, I think we can do some nice trick. Most of you may know that there's CTA Collaboration, who is building large array of telescopes in the Northern Hemisphere, in Southern Hemisphere, and in our Southern Hemisphere, a large number of Cherenkov telescopes. The last number is about 40 small-sized telescopes. And they want to measure these very high energies. You see it in the green color line on this one. And then with the 40, 50 telescopes, one can reach a collection area of 4 kilometers square. This you can read on the left-hand side. Yeah? But by using magic telescopes, very large zenith angle observations, we are coming to 2 kilometers square with no investment, essentially, for free. This is compared to CTA data at 20 degrees, while magic is measuring at 70, 80 degrees. By using this technique, we measure the spectrum of Crab Nebula until the energy of 100 tera-electron volt. And then when we compare this result with the earlier HEGRA, similar result from HEGRA, HEGRA went to a little bit lower energies. Then this result has been measured by magic about in 8 times less observations. Here we show also results from the Hawk and Lasso experiment. Also Tibet has published data, but recently Lasso published a very interesting paper where they showed that the spectrum of the Crab nebula is extending till 800 tera-electron volt, almost a peta-electron volt. I think all of us find galactic center a very fascinating object. And then even Nobel Prize was given for this reason 1 year ago. And then I think there are fascinating studies in the optical, but there are fascinating studies also at very high energies. I show you measurement of our galactic center and the ridge around it for energies at above 1 tera-electron volt. These observations are done at large zenith angles from La Palma, because you see galactic center from the Northern Hemisphere, you should go to a very large zenith angle. So the smallest angle is 858 degrees, then we measure typically down to 70 degrees. So you can see this, there are contours, green contour, and then which shows the 3 sigma signal level, and then yellow-green shows the 5 sigma level from where we measure signal. This red star shows the Sagittarius A. Green color it shows G09, well-known source, and then blue square shows the arc source, which is roughly at 0.4 degrees from the galactic center. And then please note that the white contours, it's a radio emission from the CS molecules. And this way we are tracing the gas. Now look to the right plot. This is the brightness span of a strip in the galactic center. At energy is about 1 to 1.2 tera-electron volt. And then the blue color is magic measurement. Orange is the best fit model. So what one can see, I think interesting, we see some asymmetry on this picture, left, right. We cannot yet say if this is real and what can be the possible cause of this effect. the effect is on the level of 40%. But we have more data, and with more data, we are studying this effect again. What is interesting, I think, in this issue, our colleagues from HES collaboration published a paper 2016 in Nature where they say it's a pevatron, yeah. A galactic center is a pevatron, which is a which made a big excitement in the community. And the results of this measurement you see in these green points. But it so happened that our colleagues, when measured the background in a small annulus, probably they underestimated the background. So 2 years later, they published another paper where the spectrum has been up-corrected by factor 2, maybe, roughly. You see these orange points. And in the blue points, you see the magic point. So for HES instrument, please keep in mind, galactic center is just above their head, yeah? So it's absolutely optimal for them. And we are working on the very sliding angle. So it's very interesting that our data is in very good agreement with the HES second paper, with the small with small differences that for diffused emission to be the real cause of this emission from the galactic ridge, you need a 1/r law, and we see slightly different. Instead of 1/r, you can see in this band between 1/r and then 1.5. Yeah. So once more again, I think to say a few words about the galactic center. Center of our galaxy harbors the yet closest known supermassive black hole. So we know one black hole at about 8 kiloparsec. I don't know if another black hole is known at closer distances to us. And this is a unique laboratory, of course, for studying black holes and acceleration in black holes. So essentially, our measurements are confirming results of HES with a small difference that we see a cutoff at about 20 GeV. And then, but cutoff is not so significant. It's just a 2 sigma hint. So if there will be this cutoff there, then probably I think more measurements are necessary, better measurements are necessary to clarify the issue with the pevatron. So this is an open issue. I think all telescopic installation, all 3 of telescopic installation are looking into it. And then even our colleagues on Veritas recently measured the ridge emission. So I think soon journal publication may appear. I would like now to say something totally different. So, you know, when observing galactic sources, our main aim is to understand or the origin of galactic cosmic rays. Because after 2000, in 1912, when Victor Hess had discovered cosmic rays, I think over 100 years later, 109 years later, I think we are still looking, what are the sources of these cosmic rays in our galaxy? And then I think, of course, I think there were a lot of assumptions and then theories, and then we are providing more and more measurements, and then we are very happy that there is a Fermi satellite mission who is measuring a large number of sources. So I think we are accumulating evidence. What are these cosmic rays? What are their sources? But what is true, I think we are measuring protons and higher charged ions, which we call cosmic rays. And it is interesting to see the spectrum of these cosmic rays, protons and highly charged particles until iron. Here we show you a glimpse of measurement, a very fresh measurement of proton spectrum between 1 and 500 tera-electron volt performed by MAGIC. And this data is compared with the Dampe and Cream experiments of precision data. It's very interesting to note that MAGIC data is repeating small structures above 10 tera-electron volt. And this study has been done by using machine learning techniques with neuronal networks, very specific study, which was pursued by our colleague Petar Temnikov This result will be shown in 1 week from now, starting the International Cosmic Conference. So we are intending to measure also highly charged particles. Another very interesting result, which I would like to bring to your attention, it's an extreme X-ray flares from Markadam 501. You know, Markadam 501 is a very, very famous source since at least 30 years, or about 30 years. So it is one of the brightest, very high energy sources in gamma ray sky, but it is very nearby. Redshift is just 0.034. So during a multi-wavelength campaign in July 2014, Markadam 501 displayed the highest X-ray activity observed by the Neil Gehrels Swift X-ray telescope and also by MAGIC. So the X-ray spectra displayed during this flaring episode were very hard and showed variability on nightly timescales. So on July 19, the same year, in coincidence with the peak of X-ray activity, a hint of narrow feature at 3 tera-electron-volt was measured by MAGIC. So this is very unusual measurement. At first we thought maybe we are dealing with a linear emission or something similar, but at tera-electron-volt energies, we never heard about such things. So I think the data is very interesting. We published a paper on this. And then now I think we suggest 3 different scenarios to reproduce such effect. This strong correlation between X-rays and tera-electron-volt gamma rays in a very narrow range at about 3 tera-electron-volt. This could be due to a pileup in the electron energy distribution, maybe due to stochastic acceleration, or maybe it's just a structured jet with a 2-zone synchrotron self-Compton emission model, or maybe magnetospheric vacuum gap model, plus 1-zone synchrotron self-Compton model, a pair cascade model. The last model became kind of a little bit fashionable in recent times, I could mention. So we talk about multi-wavelength observation, which is the essence of understanding emission from any given source, but multi-messenger observations is even a 1 step higher. Multi-messenger, we understand measuring different types of particles, like measuring maybe gravitational waves, electromagnetic waves, and neutrinos. And there was a very interesting measurement which has been reported by now 3 years ago. And this was a multi-messenger observation of a flaring blazar in coincidence with the high-energy neutrino. So IceCube was measured on the 17th of September, on 22nd of September 2017 at 300 tera-electron-volt neutrino. And then just within a couple of days, Fermi satellite mission measured a plausible source, very close, just on 0.14 degrees from the IceCube event direction. And just after that, MAGIC measured some signal from it. And then I think a lot of other instruments joined this study, and it was a very interesting study. The net outcome was that we can put into correlation 300 tera-electron-volt neutrino with very high energy gamma rays, and then this statement will be accurate within 3 sigma, not much more than that, but it had many consequences. And this was a first of the kind event. Just immediately after our publication, after our joint publication, there was an avalanche of models. And these models tried to see how you can accommodate emission of a neutrino and signal from a blazar, but you need a hadronic component for emitting neutrino. And then there were different models suggested for this hadronic component. Among other models, also our collaboration has developed its own model, so-called shear jet model, where you have not a simple jet, but you have a double jet structure. Where jets are moving with different speed, and then I think in this junction you can have low energy photons, which are very necessary for photo production, for producing neutrinos. So without going much into the details, I would say that we were very pleasantly surprised when last year there was a measurement of this source, plausible source for responsible for neutrino and high energy very energy gamma rays with a name TXS 0.06, 0506. And then there was evidence that in fact this source has a double jet structure. So I think I will need a little bit long time to go into details to explain what and how are important, but just I flashed the slide on the left, for example, where you can see the magic measurement and also Veritas measurement of very high energy gamma rays. And then you can see that there is a break after the Fermi collaborative measurement, and this break carries very important information. So without going into very details, if you will ask, I may try, but very high energy gamma rays and hard X-rays are very essential for constraining the models. And then the spectrum change from Fermi energies to tera electron volt. This could be either due to internal absorption of primary spectral break or production inefficiency or something else. So the favored scenario is a leptonic model with some admixture of hadronic. You need hadronic to produce neutrino, and leptonic because we measure spectrum like a two-bump structure from a blazar. Okay, few hadronic models, of course, are ruled out. So this was a very, very interesting study. It's still, the studies are still ongoing. At coming Cosmic Ray Conference, more will be reported on this topic. And I come to some very interesting result. I assume most of you are aware about this result. 2 years ago, on January 14, we were lucky in the first time to measure gigantic gamma ray bursts at the tera electron volt energies. So you can see this plot from the first publication in Nature, where data from 24 instruments are put there, multi-wavelength data. And you can see in the blue color the XRT data, and magic is shown in green color, these points. So we measured roughly 60 sigma signal roughly in half an hour. And then for the first minute, the intensity of emission was more than 130 times the emission of Crab Nebula. So there was not a single background event. It is the purest sample of gamma rays what we measured, and we could do a lot of interesting studies with this data. So then studies were very interesting because we could see in the second publication, we could demonstrate that this publication can nicely fit a double bump picture. And the double bump picture you can see now, you can see the highest energies. So what was very interesting, due to the extremely high rate, we were able to split this data into time beams of first beam was, for example, just 42 seconds. The second beam was 70 seconds. And we could measure the spectra of the gamma ray burst live, just following how it develops during time, just within minutes. I think this is incredible. I think this is a extremely strong feature of this Cherenkov telescope, because they can follow, for example, in this particular race, development of gamma ray burst with 1 minute or half a minute accuracy. So what was interesting, I think we came to conclusion that this is the synchrotron self-compton process should be responsible for this emission at very high energies. And obviously, because we found emission there, we think that BRBs have higher energy than it was supposed until now. So then I go to one more slide. Here in this slide, you can see this SSG mechanism, inverse compton emission mechanism from this gamma ray burst, which could be nicely explained. And then we think that from now on in future, the GRBs will tend to show the double peak structure. And the energy in synchrotron self-compton peak is comparable to the energy on the synchrotron. So, and then keeping this in mind, I go to a very fresh publication which appeared last month, 1 month ago, by the Hess collaboration. They had a very strong signal from GRB 1908-29A. And they measured this GRB on 2 nights. They have first night they have a strong signal, something like 20 sigma. Second night they have 5 sigma. Third night is just a marginal 2.5 hint. But I think it's a very interesting study. And then this delayed emission, they started measuring 4 hours after the onset. They measured the spectrum between 200 GeV and 3 tera electron volt with a spectrum index close to 2. So I show pictures from the publication, and then in the press release, I think I have seen a title calling "The Strange Afterglow of Gamma Ray Burst." The authors have a little bit particular view on this GRB. They claim it's a synchrotron emission responsible for the entire GRB, but then cyclotron emission was extending for over 9 orders of magnitude, and this is very unusual. This we do not know from no other source. And then they say, okay, maybe this is the case. And then what is interesting, then by 3 to 4 orders of magnitude, the synchrotron, so-called synchrotron burn-off limit is violated. This is the limit, simple limit coming from acceleration emission of electrons, where you equal them, and then you get this limit. Then the authors claim that this would require an unknown high energy process to accelerate multi-peta electron volt electrons in the magnetic fields, or a conventional acceleration mechanism in a medium with large differences in the magnetic field strength. What is interesting, another surprise came just after 10 days after the above publication. The new set of authors, they offered a classical synchrotron self-Compton explanation. You see it on the right view graph, this one. And then it's a curious situation. I think I myself am curious, and I think our community is curious to follow the further developments. So I have got the impression that synchrotron self-Compton could nicely explain the S data, but we should see forward. Then I think I would flash a few other things. So we did a Lorentz invariant study with this GRB 1901 14C data, which was published in PRL last year. Maybe you do not need that I tell you what is Lorentz invariance violation. And then I think different instruments use somewhat different techniques and methods to see if they can produce meaningful results. And then I think in the quadratic approximation, we produced the best result with our GRB data. This is of particular interest for someone if one wants to see. And then I think we published recently a paper on short GRB. We were very lucky because we made our telescopes very speckled. After 24 seconds after the onset of GRB, we had already observations of the source. So our telescopes moved in a very, very, very high speed after the alert to the third position. We got a small modest signal. And what was interesting, it says that even with Earth-Cherenkov telescopes, a short GRB should be possible to observe. And especially this was interesting, there was a hint of kilonova. The signal strength was small, just 3 sigma, measured between 600 to 800 giga electron volts. So we measured another GRB on 15th of October last year. I think with a modest signal, and then of long type. But this long type has been, this association came after 2 months after the onset of GRB, because there were speculations that it's a short type. It was very unusual GRB. Another GRB which was interesting, I think we measured the signal, was kind of a Christmas present for us. Just short before the Christmas last year, we got another GRB. We have a significant signal from this GRB, and the data will be reported in 1 week from now at the Cosmic Ray Conference. So what should I say? So I think this telescope started measuring gamma ray burst, and I think just when the first huge burst was measured, I think we understood that this may become an usual discipline for Earth-Cherenkov telescopes. Then here I want to say a few words about our future. On the right hand, you can see a photo of 23-meter diameter large-size telescope, which is located just 100-meter distance from Magic Telescope. Yeah? Here you see this is the large-size telescope, Magic 2, Magic 1. And there are 3 more telescopes of this type are under construction. And then this will be the most sensitive array for measuring energies above 20 GeV in the energy range 2200 GeV. I would say that this telescope is in its last phase before taking regular observations, and already source data from gamma ray data from about 12 sources, a dozen of sources have been measured. No publication yet, but strong results are there. So I think next times probably this telescope will operate along with MAGICs until next telescopes will be built. And this is my slide about this CTA Nord instrument in La Palma. This is how it may look like. This is not a complete picture. These white ones are Magic 1 and Magic 2 telescopes. And then next to them, there will be 4 23-meter diameter telescopes. And then recently we learned that there is a decision that 9 at middle-sized 12-meter diameter telescopes will also be built there. So I think this all is moving on, and we are very optimistic because we see that in a time scale of several years, the ORM Observatory, Roque de los Muchachos Observatory in La Palma, along with an array of 4-meter class small-sized telescopes, which will be located on Tenerife. 9 such telescopes are planned for the time being. It will become the most sensitive imaging Earth-Cherenkov telescope array in the Northern Hemisphere. And here I would stop my presentation. And thank you for your attention.
Thank you very much for this very, very comprehensive presentation. And let's see, you carry from the beginning, from the early result all the way to this latest observation, which are very, very active. What is clear that the TEV is a much, much, much more prolific region of the spectrum than we expect only a few weeks ago. Okay, and congratulations for bringing this message, and everybody will be very active, I'm sure, on this. Let's see if there is any question. At the moment, we don't have.
It's a lunchtime, and my explanations were probably not so bad, so I think well received.
Let's wait still a moment. C'è qualche novità di Dina? We have a problem because one of... Cos'è? Sì, sono loro. No, qui Islamabad. Let's see if qui Islamabad is active. The other problem is that we need still to do a ceremony with the participation of Zvi Piran and Steven Weinberg. But this, right now, for Roy Kerr, it's 11 o'clock at night, but for Piran it will be perfect. But for Weinberg is too early. Therefore, did you check with Pirani? Okay. It's not. Sì, risponde. Chi? Allo?
Avevo anche lì.
Yes. E voi cosa vuol dire conversazione permessa?
Che gli hanno dato il permesso di fare una domanda di
Deve parlare. Roy? Ok.
L'ho scritto a 5.
Ok.
Is this Remo Ruffini?
Okay.
Who is the Roy? Roy. Roy?
Please say yes. Start. At the moment, let me go. He's to. Please start. You can start. No.
Okay. We have.
We take over now or not?
Yes.
We take over.
Okay.
Thank you very much, and welcome to the next session, Oleg Beg's Universe. Before I start talking about Oleg Beg's Universe, let me say a few words about Abdul Salam, the Nobel laureate from Pakistan, who did so much for the development of physics in the third world, and also, of course, in Pakistan. And in particular, he developed the International Center for Relativistic Astrophysics, for theoretical physics, which is the role model, perhaps, for the International Center for Relativistic Astrophysics. And with that, he developed a number of programs for improving science in the third world. In particular, he had a program of networks started, and there was the network that I was in charge of for other places, included with Uzbekistan. And a conference was held in Uzbekistan, and I went and I saw the Ulugh Beg Observatory in Samarkand. And I also helped to try to develop the science at the time there. They had problems. And we managed to get a lot done for science in Uzbekistan on the base of the International Center for Theoretical Physics. And that has taken off in itself in a big way. We have managed to get a lot from Salam, and it was important that he should be commemorated and remembered in this conference, particularly for the Ulugh Beg session, and particularly for CUI, because we are trying to pursue a seat for the International Center for Relativistic Astrophysics at this ComSats University, Islamabad, where we're meeting now. And from here, we will be trying to arrange that all of Pakistan can participate in the International Center for Relativistic Astrophysics, and that it could be then ultimately named the Abdul Salam Center for relativistic astrophysics. Well, this is a plan, hopefully for the near future. We're trying hard to get it done as fast as possible. So, having mentioned Salam and his tremendous contributions, not just to science, but to the development of science in the third world, and to the way it has encouraged cooperation in the scientific community worldwide among all scientists. And that really encourages for peace. So his contributions are immense. His name means servant of peace, Abdus Salam, and he was indeed a servant for peace. Let me now go on to talking about the Ulugh universe, as it has been called, but not as Ulugh knew it at the time. I would like to proceed on now with the talk. And we're commemorating here a medieval astronomer who worked on the world's leading observatory, Ulugh, and there'll be a talk after mine, which will be talking in more detail about the science from there. People may object that in a meeting on the cutting edge of relativity and astrophysics, there's no need to hark back to medieval times. But I say there is need, lest we forget. Developments in the area of investigation take place in the context of past developments. And losing contact with what has gone before, we can drift off into directions that are not relevant or useful. This applies to astronomy and to the study of motion that we call dynamics, be it the old Newtonian or its Einsteinian modification, relativity, or that of Heisenberg and Bohr of quantum mechanics. Ulugh from 1394 to 1449 was the grandson of the Mongol conqueror Tamerlane and built the largest observatory of the time. Though it is credited with an accuracy of 3 arc minutes, when I went and saw it, my estimate was a fifth of that, because the separations are large, and by eye you can look at the finer estimate for that. It was this accuracy that provided data that would later be used by Copernicus, 1473 to 1543, for constructing his heliocentric view of the universe as known at the time. This was subsequently used by Kepler, 1571 to 1630, to get elliptical paths for the planets, which, with Galileo's telescope, was used with the reflector telescope by Newton, 1643 to 1727, to obtain his law of universal gravitation. One of the problems of the day is that the two theories deriving from Newton's dynamics do not match. Instead of looking back for the answers, people have been wildly speculating about many extra dimensions and new types of symmetries. My present concern is not with that, but with the observed exponential expansion of the universe and the wild speculation of, as they call it, a mysterious dark energy. Once again, lest we forget, let us look back. Generalizing special relativity. That is where Einstein had started. He presented his special relativity in 1905, actually the special theory of the relativity of simultaneity. Not everything is relative according to that. Simultaneity is relative. The whole idea of the theory is to find absolutes and not to talk about everything being relative. This resolved the outstanding problems of electromagnetism in 1905 in a trivial way, but it only worked for uniform linear motion. When his teacher, Minkowski, wrote the theory in geometric terms, this was in 1907, Einstein did not appreciate it and commented that it contributed nothing to the theory. Einstein continued with work on the restricted theory, the special theory, but by 1908, he had realized that by considering uniform circular motion, that to generalize the theory, he needed non-Euclidean geometry. His argument, given in my book, is that as the length along the direction of rotation shrinks, but is constant along the diameter, the ratio becomes less than pi. And so if it becomes less than pi, you no longer have the geometry of Euclid working. As such, Einstein had to adopt the much hated geometry. Since Einstein had skipped the geometry classes at his university, which were taught by Minkowski, he went to his friend Marcel Grossman. This is the Marcel Grossman meeting for precisely this reason. It was a major contribution from Grossman that led to it. In fact, I'll bring out how major it should be regarded as. To teach him geometry. After blundering around with other geometries, they hit on the use of differential geometry. In Minkowski's four-vector formalism, an observer moves along a time-like path that is assumed to be a geodesic, shortest path, for free particle motion, and looks at a test particle on another time-like geodesic to see its motion. If the space-time is curved, the geodesics will also be curved, and the path will be bent as if due to a force. Now that you could actually see by thinking of the surface of the Earth and see lines of longitude, and then you see that the lines of longitude diverge from each other. But then over time, the divergence reduces and they go parallel and then they start converging. So you can see the effect of curvature coming in there. I'll be talking a bit more on that later. Aristotle, in circa 350 BC, believed that space was only defined by matter and not on its own, as a distance between material objects and time as a measure for chronology of events. In his Principia Mathematica, Newton defined an absolute time and an absolute space independent of matter. People, I claim, got brainwashed into believing the Newtonian picture, but it requires a mystical force of gravity acting at a distance. You see over here, here is this, I don't know, this doesn't really come up well. No, it doesn't show that. I'm not sure. Can I have that, because this is not doing the job well. There's no use here. It can't be. I mean, I wanted that with me. I need to use it. Thank you very much. So, you see, there's this particle here, this little body. Supposedly it just gets pulled to this. This big body waves its arms at it and it just gets pulled in. Well, that is a mystical idea. Instead, just see how the space-time curvature gives the effect of a force on the smaller body in the vicinity. Look at the bending of the path over here, because when this gets bent, this body won't go straight along as it was doing. It will go along the bent path and go towards the big body. That is the other way of seeing the force. Newton called this a force, but just think again, how could the bigger body, if you forget this grid, and just see that small little body being pulled to the big body with nothing doing it. You just, I will you to come to me and you will come to me. That doesn't make sense. Aristotle's and Einstein's is the more natural way, the physical way of looking at it. If we had not had this brainwashing that there's a force that acts at a distance directly. That, though Newton English propaganda did it. Okay, so the derivation of Einstein's field equations is credited to David Hilbert and Albert Einstein in 1915. Hilbert, by using the Einstein-Hilbert-Lagrangian, had published the paper before Einstein's. It had appeared before. And it may be argued that Hilbert should have prior claim to the theory. However, Einstein was a physicist and he delayed submission to obtain the prediction of the perihelion shift of Mercury, while the mathematician Hilbert did not bother with the physical test of the theory. Yet everybody regards general relativity as Einstein's theory, not Hilbert's at all. The recent book dedicated, among others, to Remo Ruffini is entitled Einstein's General Theory of Relativity. Why? There'd been earlier work by Einstein and by him and Marcel Grossmann that presaged the derivation of Einstein's field equations and general relativity, which has been ignored because people did not look back and forgot. Einstein had already had his breakthrough realization that space-time seen in free fall would be flat, but in other frames, gravity would give curvature. With Grossmann, he had proposed that the metric tensor needed to be used to replace the Newtonian scalar gravitational potential with a 10 independent component tensor potential, and discussed the covariance of the theory in 1913 and 14, as you see. So well before the 15 that he had got the work with at the time that Hilbert did. Though Einstein and Grossmann never published the next steps, which I'll be giving here, for the derivation of the Einstein field equations from the equations of motion, I believe, and I'll give reasons for it later, that Einstein already had this in mind. In a curved space, two geodesics seem to diverge at a varying rate, like the distance between two lines of longitude on the surface of the Earth. This can be seen more rigorously, and I hope you'll bear with me while I give a little bit of mathematics there. Two of a family of geodesics, there's one geodesic gamma I, the other geodesic gamma j, having unit tangent vector t, this one. Like on this one, this. So these are the two geodesics. There's one observer, me, And at one time, P, I see you, Q, at some distance. So I'll say this is your position vector P. This time taken will be unit vector time t, and this is the time direction. As this line curves, so this unit vector will be tilted around, and when I get to R, I'll look at U and I'll see U at S. So this is still the position vector P for you. So this is a vector field which is changing. Now, this is called Lie transported. If I take it that you see to go from here to here, this goes from here to here. It continues to go along, I keep on seeing you. That's the way that would be defined. If instead I were to flatten out this geodesic onto space, then I would have the parallel transport, and then I'd have this thing, the equal magnitude over here, and so it would be this size rather than this. This would be the parallel transport, this would be the Lie transport, and there'll be a difference between them. And that is going to be important. Acceleration is the second derivative of the position vector relative to time, and the derivative relative to time is observed by applying the unit tangent vector. I've used Penrose's abstract index notation, but you don't have to worry too much about it. This is just the vector itself. These are not component indices. These are just the vector P, the second derivative P as the vector, not the component. And there is the vector T acting on the vector T, acting on the vector P. That will be the acceleration, because T acting on P will be dP by ds, and d square P by ds square will be T acting on P. And so that will be what we're wanting to talk about, and that's the derivative of P. Now, this notation is not so familiar, but this notation is familiar. There's the usual tensor notation, and so there's the covariant derivative, and now I can say that if P is Lie transported, I can shift the P here and shift the T here. So then this becomes equal to this. Now I can expand this out, the covariant derivative on this and the covariant derivative on this. One is on the P, one is on the T semicolon D. And so I'd get this. Now I could again do the same thing I'd done here. I take this P over here and the T over here. And now I could take this semicolon C out over here, but if I do so, I get a TA semicolon D semicolon C, which I have to then subtract out. I do that, then I've got this derivative. This is Riemann's definition of the measure of curvature. So what I've said is the acceleration is related to the curvature. Dynamics comes from geometry. That was the beauty of what I think Marcel Gossman and Einstein had already seen. Einstein had realized with the rotating disk and later with a falling lift leading to the gravitational deflection of light that the space-time appears curved to accelerated observers. With Gossman, he realized that space-time must be curved in the presence of matter. As Wheeler put it, matter tells space how to curve, and space tells matter how to move. The natural step would be to relate matter and curvature. Since 1905, Einstein had already got matter and energy identified, the mass equivalent to energy. And so the distribution of matter and energy is given by the stress energy tensor T mu nu. You don't separate off just matter, which Newton had just matter by itself, but matter and energy will have to be put together. So you'd have the stress energy tensor, and it must be related to the curvature tensor by some function. So you take the simplest possible function. Well, the simplest possible would just be a constant, which would throw the baby out with the bathwater. You'd get nothing if there's a constant. It doesn't tell you anything about the gravity. So the first non-trivial attempt would be this function over here. And that is what is to relate this T mu nu to R mu nu. And so if I just take that kappa the other side, I define lambda dash is kappa inverse lambda, I'll have this equation, which is the Einstein field equations. Notice the constant of integration is required here. So that is crucial in my opinion. It is generally assumed that Einstein derived these field equations by using field theory. However, I disagree. I think he used the derivation that I've just given. And why do I say that? The published paper uses the Einstein-Hilbert-Lagrangian. However, in his notes, earlier versions have the constant term equations. People have argued that Einstein had not actually derived the equation and he got it from Hilbert. I suspect that he knew that the geometrical derivation would not be understood or accepted by the physics community, which was used to see in field theory. As such, he needed to get the field theoretic derivation and did so with a constant added to the Lagrangian. Unlike Hilbert, he needed a physical check. His equations predicted the missing perihelion shift of Mercury without using the cosmological constant. I think he felt that if he published his theory with the extra term, people would object that arbitrarily setting the extra phi parameter to 0 negated the prediction, and so he suppressed the constant term. Later, when Einstein wanted to see his theory not as minor corrections, but as the dominant ruling theory, because of its nonlinearity, he needed to apply it to the universe as a whole. However, when he did so, the theory was non-static, and he believed that the universe was static. He therefore reintroduced the constant as the cosmological constant, which is then causing a repulsion in expansion. What difference does it make whether the constant arose as a constant of integration or as a constant term added to the Lagrangian? The difference is that in the former case, we would regard it as a part of the theory. And so, like we appeal to experiment for the gravitational coupling, we would appeal to observation for the value of the new constant at the scale of the galaxy. It is too small to be observed, but at the larger scale, it is seen. If it is introduced as part of the Lagrangian, it is a vacuum energy, and we should use quantum gravity to work out what the vacuum energy would be. Unfortunately, there's no problem-free theory of quantum gravity. In the absence of a genuine theory, people appeal to dimensional analysis for the onset of quantum gravity. Since 1/c, g and h going to 0 give the classical limit of special and general relativity and quantum theory becoming classical, all must play a role as they are all significant. The quantity with units of energy constructed from here gives this, which is 10 to the 19 GeV. while it is correct that by this quantum theory, quantum gravity cannot be neglected, there's no basis to say that the onset will be at this energy. However, it is then argued that then the cosmological constant, being a vacuum energy associated with gravity, must be of this order of magnitude. There's no logical nexus to this argument. While speculations lead to many more publications than those based on scientific evidence and accepted theory. John Wheeler used to say, I would not change my bank because it made a tiny slip. But if the purpose is to have as many accounts as possible, then you would change it. A claim was made that the quantum vacuum space-time is unstable, but this was proved wrong by Hussain and Qureshi, his letters. So there's no good reason to speculate on models of dark energy with contradictory attributes. Lest we forget, let us look back. Thank you. And now, if there are any questions, I would be happy to answer them. But I don't know, can we get to another mode? This thing is still here.
Thank you very much. There is any question?
Any questions? Yes.
That was very thought-provoking.
Well,
maybe, Ashkar, since you kept your time perfectly, can you introduce Bagheri?
Sorry, I didn't hear that.
Can you introduce Bagheri for the next lecture?
Yes. Go ahead with the next lecture. I just need to now introduce the speaker for the next lecture. The speaker is Professor Muhammad Bagheri from Iran, and he is a historian of mathematics and astronomy. He's chief editor of the Persian journal Miras, Scientific Heritage, and member of the Scientific Board Institute for the History of Science. His PhD was in electrical engineering, but he received his PhD in history of mathematics from the University of Utrecht in 2006. He is also active in the popularization of science, and his scientific hobbies are sundials and origami. He is going to be talking about Ulugzbek's scientific school. So, Dr. Bagheri.
Okay, can I start?
Yes. Yes, please.
Buongiorno. Buongiorno amici e cari amici e colleghi. Hello everyone. I will give my talk entitled Ulugzbek's Scientific School in Samarkand. Ulugzbek was the grandson of Tamerlane, who conquered a vast area in Transoxania and Central Asia and Iran around 1400 AD. Ulugzbek was born in 1394 in Sultaniya, near present Zanjan, city of Zanjan in Iran. Nowadays, there is an active center for higher studies in Zanjan, which is internationally known in the field of mathematics and astronomy. I was connected to this conference through Professor Youssef Sobouti, the founder of this creditable academic center. In 1409, Ulugh Beg became the ruler of Samarkand, where he founded a school in 1420, which is still well preserved there in the famous Registan Square in ancient part of Samarkand in Uzbekistan. Astronomy was the major subject taught in the school, and Ulugh Beg gathered a group of astronomers there. He also founded an observatory in 1424, which was designed by the Iranian scholar Jamshid Kashani, best known as Al-Kashi in the West, who, upon Ulugh Beg's request, supervised the construction and operation of the observations made there. Jamshid Kashani is also famous for his very accurate calculation of the number pi, the ratio of circumference to the diameter of a circle. After Ulugh Beg's tragic murder arranged by his son in 1449, the observatory was destroyed and forgotten. Its remnants were rediscovered in 1908 near Samarkand. The main part of the observatory was a huge stone sextant more than 40 meters long. It measured the meridian transit of celestial bodies, from which the declination of the ecliptic epsilon, which equals to 23.5 degrees, the equinoxes, and the geographical latitude of the locality could be determined accurately. The results of the observations were composed in a Persian treatise called Zij Ulugh Beg. Ulugh Beg also devised a method for finding the sine of 1 degree, for which he solved a cubic equation by a method now called fixed point iteration. Its manuscript is lost, but the method is described by the commentators of Zij Ulugh Beg. Another scientific work from Ulugh Beg is an Arabic treatise on parallax, which has never been mentioned and studied. One of my young friends is working on that treatise. Zij, I mentioned Zij Ulugh Beg. Zij is the Arabicized form of the Persian word zig, used for a collection of astronomical tables with explanations for using them in astronomical calculations. In the process of the translation of Middle Persian, it is pre-Islamic Persian astronomical texts, into Arabic, the word zig was changed to zij. And in the process of the translation of Arabic astronomical texts into Latin, it was Latinized as zich or ezich. During the period from the 9th to 15th century, around 200 zijes, or collections of astronomical tables, astronomical numerical tables with explanations. 200 zijes were composed in the context of the Islamic civilization. They were mostly Arabic and Persian, with some samples composed in Turkish. The early zijes were influenced by ancient Iranian and Indian astronomical traditions. For example, Muhammad Khwarazmi, who lived in the 9th century, composed an Arabic Zij in the Indian tradition, which has not come down to us, but remains in a Latin translation of an abridged version, which was prepared by a Muslim astronomer from Madrid around 1000 AD. After the introduction of Ptolemy's Almagest into Islamic astronomy, Almagest was translated into Arabic. Most Zijes were essentially influenced by it and followed its methods and parameters. However, some modifications were also made to Ptolemy, like Kushyar ibn Laban's interpretation method for calculation of interpolation method, for calculation of the true longitude or ecliptic longitude of the planets. Kushyar ibn Laban lived in Iran around the year 1000 AD. Some of the Zijes were based on independent astronomical observations. However, many of them were based on former observations with modifications for locality and precession of equinoxes. One of the important Zijes composed in the Islamic civilization is the one composed by Battani in Mesopotamia around 900 AD. It was in the tradition of the Almagest, and many later Zijes were influenced by it, including the Zij of Kushyar ibn Laban, whom I mentioned before. A Latin translation of Battani's Zij with an edition of its Arabic text and ample comments has been published by the Italian scholar Carlo Alfonso Nalino in Milan in 3 volumes in the years 1899 to 1907. Another Latin translation was already published in 1537, and a second Old Latin translation was never published. You see, there have been 3 Latin translations of the work. The late American professor Edward Stuart Kennedy prepared a descriptive catalog of the Zijes with useful and comprehensive explanations in 1956. It is entitled A Survey of the Islamic Astronomical Tables. It was reprinted in 1989, I mean, after about 30 years. And Dr. Benno van Dalen from the Bavarian Academy in Munich is preparing an updated version of it. I have published a Persian translation of this work in Iran in 1995. Ulugh Beg composed his Zij around 1435. Ulugh Beg used the results of astronomical observations of a group of astronomers who worked in the observatory of Samarkand. Hundreds manuscripts of this work are extant in the libraries and manuscript collections of several countries. This shows that Ulugh Beg's Zij was very popular in the whole Islamic civilization. Its partial Latin translation was published by John Greaves in London in 1650. 15 years later, Thomas Hyde published another partial Latin version of the work in Oxford, England. Around 2 centuries later, the French scholar Sédio published the first part of the work with French translation in Paris in 1847. 70 years later, in 1917, Nobel published the Star Catalogue of Zige Ulugbek in Washington. The Russian translation of the Zige Ulugbek was published in Tashkent, Uzbekistan in 1994. The Uzbeki, English, and Chinese translations are planned to be published in Tashkent in 2022, the next year. Several commentaries have been written on Ulugbek's Zige. All these, so this number of manuscripts, these commentaries, the translations, all these show the popularity of Ulugbek's Zige in the course of centuries. It was actually used by Iranian traditional calendar composers during these centuries. However, in the course of time, the accumulated errors due to approximations in the tabular values led to noticeable deviations between observed phenomena and calculation results on the basis of Zige Ulugbek. In 1838, a Persian Zige entitled Zige Bahadur Khani, named after a certain Bahadur Khan, who was a ruler in north of India. This Zige Bahadur Khani was composed in India by a certain Ghulam Hussain Jumpuri. He was from Jumpur, a city near Banaras. It was published as lithoprint around 20 years later, from 1855 to 1858 in Banaras, North India. After the appearance of this Zige, the Iranian traditional calendar composers preferred to use this one instead of Zige Ulugbek because it was based on more recent astronomical data produced from new observations. Junpuri sometimes refers to the achievements of the modern European astronomers, but he follows the traditional Ptolemaic patterns which were dominant in most of the former similar works. Ulugbek has started his Zige with a section on calendars in which he provides tables for Hejira or Arabic, Yazdegerd or Old Iranian, Seleucid or Old Greek, Maliki, Iranian, and Chinese Uyghur calendars, and the methods of converting them to each other. He also provides tables for the trigonometric functions sine, tangent, and cotangent. He gives tables for declination and inclination of the points on the ecliptic. He also gives tables for right ascensions and oblique ascensions, calculated for the latitude of Samarkand, the site of Ulugbek's observatory. These tables include columns for differences of consecutive function values which were used for interpolation. There is also a table for the equation of time as a function of the true longitude of the sun. I was recently informed that a student is doing a BSc, bachelor thesis, in the University of Utrecht with Professor Jan P. Hogendijk on the discovery by Carl Friedrich Gauss of the method of least squares and its first application on the table of equation of time by Ullrich. Gauss did this work in 1799 when he was only 22 years old. Professor Hogendijk from University of Utrecht has created a website entitled the Samarkand School in Astronomy and Mathematics. Its address is www.samarkand.eu. Mean motions of the sun, the moon, and the 5 known planets of his time are tabulated for the years 1437 to 1466 AD. In addition, motions of these celestial bodies in multiples of 30 years up to 900 years are given. There is also a table for the correction corresponding to the change in terrestrial longitude. These are followed by tables of equations. Equation here does not mean the ordinary meaning of equation. This is a special term in ancient astronomy, which means modification. These are followed by tables of modifications or equations for finding true longitudes and tables for finding ecliptic latitudes of the celestial bodies. There is also a table computed for stations and retrogradations in Ullrich Siege. There are tables for solar and lunar parallax in the latitude circle. In the section dedicated to the eclipses, there are tables for radius of the sun, the moon, and the shadow of the earth. There are also tables for the visibility of the moon and the planets, the geographical latitudes and longitudes of 240 locations, and the ecliptic coordinates of the fixed stars. Most of the star coordinates are the results of independent observations, and some of them are Ptolemaic values with the longitude corrected for precession of equinoxes. The star table has been published by Nobel in Washington in 1917. Some of the above mentioned materials, especially in the field of astrology, are taken from former sieges. For more details, you can refer to the book by the late Professor Edward Stuart Kennedy, A Survey of Islamic Astronomical Tables. An English translation of the astrological part of Ziji Ullrich was published as a small booklet in Tashkent around 25 years ago. Now I want to say some words about Ullrich as a knowledgeable and humane ruler. Before that, I want to mention that in spring 1995, I was invited to Uzbekistan to attend a gathering in honor of Ullrich. Together with 2 friends, we traveled the long way from Tehran to Tashkent. We passed Turkmenistan, Bukhara, and Samarkand. On our arrival in Tashkent, we were informed that the conference is postponed for some weeks. Our visa was not valid for that date. We tried to extend our visa for this purpose, and our colleagues in the Ulugh-Beg Astronomical Institute in Tashkent did their best to extend our visa, but in vain. It failed. After returning, so we could not attend actually the conference. After returning to Iran, one night, late in the night, when I was putting in order papers relating to that conference, I discovered that among the manuscript copies relating to Jamshid Kashani, who worked with Ulugh-Beg, there is a copy of a letter Kashani had sent from Samarkand to his father who lived in Kashan in Iran. In fact, a letter of this kind was already known and had been translated into English 2 times, into Arabic and Russian. However, what I had found was another letter which had never been noticed. Some materials were in common between the 2 letters, the already known letter and the newly found letter. But there were new, invaluable, very precious information in the newly found letter. I confess that that night, really, with great excitement, I could not actually sleep. Both letters are, apart from personal materials exchanged between the son and the father, first-hand reports of the scientific activity in Ulugh-Beg's school in Samarkand. I translated this letter into English under supervision of Professor Jan P. Hogendijk from the University of Utrecht, the Netherlands, who later became the supervisor of my PhD dissertation. The translation, the English translation, was published in the journal Historia Mathematica in 1997, 24 years ago, and received a noticeable appreciation. The newly found letter has also been translated to Italian, thanks to my friend Dr. Claudio Cecotti, but it was never published. Professor Cecotti is my Italian friend living near Udine, and he has translated an important astronomical work from Biruni, the great Iranian astronomer from 10 centuries ago. He has translated also this into Italian, and in the amateur astronomical society of Udine, I gave a lecture in Italian about this letter. One important piece of information in this new letter is Kashani's strict assertion that the Samarkand Observatory's main body was a sextant like that made by Khojandi around the year 1000 in Rey near present Tehran. Now this one is destroyed. Before the discovery of Kashani's letter, some scholars believed that the main body of Samarkand Observatory was a quadrant. I finish with Kashani's appreciation of Ulugh-Beg's capacities. In the letter to his father, Kashani writes, "Now I will mention the king's skills. First, he knows Arabic syntax well and writes Arabic elegantly. He knows Arabic, Persian, Turkish, Mongolian, and some Chinese. He knows by heart all the glorious Quran, the sacred book of Muslims, and knows well the commentary and citations thereof, thereby making apt quotations therefrom when speaking. He has memorized all the dates, for example, of events which occurred during his life. He knows the art of prosody and versification extremely well. His fantastic memory is one of the wonders of the world. For instance, one day he sat down and began recounting all the places and dates of his residence since he had been in Sultaniya, telling, for example, what day of the week and the month it was when he and his party left such and such locality, halted for noon prayers at such and such place, and leaving there when and where they traveled by night and where they halted next. He thus came to the point of narrating what the envoys and spies had reported to him during the trek. He had the diaries of that long journey brought to him. We were listening, the diaries accorded with his narrative. Again, he continues, he has great skill in mathematics, Olobe. For instance, once when he was out hunting while on horseback, he wanted to determine exactly when in summer or winter had occurred an event which was known to have taken place on a Monday between the 10th and 15th of the month Rajab of the year 819. And he did it by mental calculation very easily. Grazie mille. Thank you very much.
Thank you very much, Professor Bagheri, and thank you also for the present that our common friend in Subhuti has made in organizing this beautiful lecture. And I'm sure Subhuti has enjoyed as well, because after all, it's a beautiful center for advanced study in which everybody enjoyed to visit from all over the world. And I'm sure that it will flourish more and more in the future year. And we like very much to keep in touch and help wherever you can. Thank you again.
You are welcome. Prego.
Since this morning, I am Let's see if Kerr is there. Yes, Roy is there.
Yep.
Okay.
Can you hear me?
Yes, Roy, you have been a hero. Zvi, are you in?
I'm there, but I cannot start my video. Can you enable me to start my video?
Definitely. Let's see.
Ghost asked you, okay, start my video.
Here, oh, yes, you
see.
can. Oh, very, very nice.
Yeah.
I don't know the situation.
This is the background is my working place.
Okay, I'm online.
And I don't know if Stephen can be reached. We have made all possible effort, and if we have no connection, I think we will proceed and we will record all the document and send to him the award together with this YouTube presentation. Is that okay with both of you? Roy, then can we start with the...
Yeah. Are we starting now?
Just a moment.
Okay.
Gregor. Cosa succede? Vai.
Sto condividendo lo schermo, così può vedere il libretto degli award in diretta.
Gregor is trying to connect. Oh, okay. Are we there? Can we start?
Me?
Yes.
Me? Now, okay. Well.
No, Gregory has still a problem. Premeresco fare clic per uscire dallo schermo interno. Okay, I think I have, you can see, yes.
Yes, I can see.
Okay.
Okay.
You can hear, yes? Okay. Yes.
I can't see Professor Paran.
I'm here.
Yes.
I'm here.
He's there.
Hello.
Hello.
Well.
Okay, here you are. Next one to the other. Can you see?
Yes.
It's just on your left.
The the 2021 individual Marcel Grossman Award was going to Professor Paran for extending relativistic astrophysics across international frontiers, a true companion in the search for the deeper meaning of Einstein's great theory. Paran's research deals with numerous aspects of relativistic astrophysics, ranging from the foundation of numerical relativity to modeling of observer relativistic phenomena and analytical work on the fate of gravitational collapse. Paran's research work focuses mostly on black holes, and in particular on gamma ray bursts. He was amongst the first to point out their cosmological origin and their association with merging neutron stars and heavy R process nucleosynthesis. Paran's achievements were recognized in the 2019 EMET Prize for Physics. Thank you, Professor Paran.
Thank you very much, Sweet. Maybe I will add a few words. I don't know if I can have the picture that I have on the booklet, which is common which is common both for Zvi and for Steven Weinberg. Therefore, let's see if I can recover these images. A moment. I mean, posso vederlo? Il testo? They are the beautiful images that people can look on the booklet. But we are celebrating this MG16. It's a very special occasion, not only because it's the first one that we have electronically connected and not in person, but the number of participants is similar, but also because it covers a long activity of the Grossman meeting, which were started in 1975 at the ICTP in Trieste, and with the participation of Abdus Salam, of course, around Abdus Salam. The second meeting in 1979 was also organized with Salam, but with the advantage that Salam had very, very good contact with China and with Zhou Enlai. And for the first time, we had a participation, very nice participation of Chen Ni Yang. By the way, Chen Ni also received a few years ago the Marcel Grossman Award in a continuation, and a delegation from China led by Zhou Peiwan. And I have enclosed a picture which is very nice, in which you have on the second row Zhou Peiwan and Xian Yang, and just in the back of it, oh, here we are, good. And in the back of it, here you see Lishnerovitz with another person. This was a very successful meeting, but was still localized around Trieste and Italy. And then the bold idea came to make a big jump for the Marcel Grossman meeting. The jump being to have the third meeting in 1982 in Shanghai, in China. This step was very important, as we will see, both for our meeting and for China. If you, in those days, if you were visiting China, and I did that prior to the meeting, of course, there was a motto in China written all over the place: friends from all over the world are welcome. This was a multi-millennial attitude of the Chinese civilization. But we soon found a problem, because friends is not clear in which term should be applied. And we soon realized that there was a constraint. Friends could be only with a country with which China had diplomatic relations. And since China did not have at the moment connection with Israel, the idea to have Israeli scientists was not allowed. And that time, I remember distinctively, and this is the reason why we formulate an award also for Steven Weinberg. Steven, with the usual frankness, called me up and said, either you solve the problem of the Israeli participants or we boycott the meeting. This was a strong statement, since Steven had been one of the co-founders of the meeting. But I appreciate the constraint and discuss a lot with another fantastic person at the time who was a member of the committee of MG Meeting, Yuval Ne'eman, which was not only a great friend, but also the Minister of Research at that time, in addition to all the other enormous important activity. And then Yuval, here is a nice picture of myself, Yuval, with the president of Chaim Weizmann, the president of Israel. By the way, at that meeting was also present Claudio Teitelbaum, and was particularly touchy to speak with the president about his mother, who was also Weizmann. Apart this, this beautiful occasion to be with Yuval, which we had for many years, Yuval gave a boundary condition, at least one. Therefore, I went with this message to Beijing, a little bit not realizing the complexity of having a discussion with with Chinese. I was confronted with 13 people in a beautiful villa, isolated, not too far from Tiananmen. And every morning we were meeting with these 13 people facing me, asking all sorts of questions. Why this man who has a Canadian passport does not come with the Canadian passport? And then I said, well, ask them. But it was clear to me that they were extremely, the Chinese colleague, Cho Pei-wan, and also other who were in the delegation, well informed about Israel and about the general international scientific community related to Israel. And we kept going. I had the 3 books of Matteo Ricci, Rimato, with me. I was just reading the Rimato story and then stubbornly going to each morning to the meeting, answering questions, making all the possible effort, but ever giving up. And we kept going this discussion until Saturday morning. We were packing with Fang my luggage, in very sorrow to have not succeeded, ready to cancel. But then at the last moment, we were convened by the foreign minister of China with a message which started, a very beautiful message starting, in view of the friendship between Italy and China going back to the Silk Road. In view of the great tradition of friendship with Rimato. And then, until recently, with the friendship between Fermi and Xian Yang and T.D. Lee, we will allow 2 scientists from Israel, 2. I had a constraint of 1 from Yuval, says positive. But then the second clause came. They should not be politically involved. This implied that Neyman could not come, but Neyman was ready not to come. Actually, okay, let's go on. Then we kept going that be young. Of course, young doesn't mean anything in China, because I was speaking with one of the founders of the University of Hefei, and he was 92, and he convinced ourselves that he was still very young. Therefore, after discussing with, visiting with Amaldi and visiting him, I realized that indeed Amaldi was very young, but he convinced us that 92 is still not an extreme age. And then we went on, therefore that was not a real constraint. And then finally came the constraint on any document agreed between Remo Ruffini and the ambassador in Rome. And they asked which kind of document would be appropriate. And they answer, we don't understand the question, you have to decide. Then we decide on a new document with picture, born in Israel, living in Israel, and the document was signed by, under my request, by Abdul Salam. Therefore, Gerald Tauber was one of the 2 persons with whom I kept. I put a beautiful picture of this meeting in Sicily. And I put this picture not only because Tauber is there, but there it's one of my closest friends for all my life, which is Arrigo Finzi. And also Gerard Bloiler were there. And I have still in my heart the memory of Arrigo, who helped me. He was a professor in Rome, young professor with the thesis with Levi Civita. Before Levi Civita was taken out, cancelled from the academies and from using his office, a tragedy of Sapienza, which is not new to these actions, unfortunately, what we are living in these days. And Arrigo explained to me a lot of things about that terrible period. And then, of course, we met again in America, and then later Arrigo went back to Haifa, and I enjoyed visiting him many times there. Therefore, the people selected were Tauber and Tzvi Piran. Therefore, with this document, Tzvi came, but was much more important, this happening for China and for MG meeting, because indeed it was the first international meeting, like Chope 1 used to understress, the first international meeting in China. And many people were happy because from then on, the freedom to invite scientists and the world, friends from all over the world are welcome, was started to be used differently. Scientists for all over the world are welcome. Therefore, in this sense, I think Stephen was the one to force us to do something extremely important for science, extremely important for everyone, for China even, and also, of course, for the Grossman meeting. And I remember always when I arrived in Princeton, John Wheeler gave me a picture in which he was walking together with Einstein and Hideki Yukawa. And he signed that picture to Remo Ruffini, companion in the search for a deeper meaning of Einstein's great theory of great theory, with warm personal regard, John Wheeler, April 1968. I have this picture here at ICRA and ICRANET. And everybody can see on the entrance, and I formulate therefore with the same wording to Zvi and to Stephen Weinberg. Little different, but not too much. Maybe Roy, you can read the different wording in the case of Stephen, in the case of Stephen Weinberg, in the case of Zvi. Can you read them?
For Stephen, for Professor Weinberg?
Yes, for
the 2021 Marcel Grossman Individual Award is going to Professor Stephen Weinberg for unwavering support for the Marcel Grossman meetings since their inception, a true companion in the search for the deeper meaning of Einstein's great theory.
The same wording that we have used with little difference for Zvi, and the simple wording, the wording which relates ideally to Johnny, to Yukawa, but especially to Albert Einstein.
Thank you.
Okay, Zvi, can you say a few words, maybe?
Yes. Stephen Weinberg is a member of the Physics and Astronomy Department of the University of Texas at Austin. His research has covered a broad range of topics in quantum field theory, elementary particle physics, and cosmology. He has been honored with numerous awards, including the Nobel Prize in Physics, the National Medal of Science, the Heinemann Prize in Mathematical Physics, and in 2020, the Breakthrough Prize. He is a member of the US National Academy of Sciences, Britain's Royal Society, and other academies in the USA and abroad. The American Philosophical Society awarded him the Benjamin Franklin Medal with a citation that said, "He is considered by many to be the preeminent theoretical physicist alive in the world today." His books for physicists include Gravitation and Cosmology, the 3-volume work, The Quantum Theory of Fields, Cosmology, and published in April of this year, Foundations of Modern Physics. Educated at Cornell, Copenhagen, and Princeton, he also holds honorary degrees from 16 other universities. He taught at Columbia, Berkeley, MIT, and Harvard, where he was Higgins Professor of Physics before coming to Texas in 1982. The 16th, no, I will stop there and congratulate Professor Weinberg on this award. Thank you.
Professor Piran.
And Professor Piran. Sorry.
Thank you. I want to thank the organizers for giving me this honor to get this award. And I would like to begin just by showing one thing which is related to what Remo just said. I hope you see this.
Yes.
This is the visa with which I entered China. You could see I looked quite different. There was a somewhat different amount of hair on my face. And this was, you can see here at the top, International Center for Theoretical Physics. This is the signature, this is the stamp of the Italian consul, of the Chinese consulate in Rome. And this allowed me to be only in Shanghai. This is Shanghai's destination, Shanghai, and it allowed me to be only in one place, only in Shanghai. Later on, during the conference, there was a small crisis because there was a conference trip to Suzhou, which is nearby, and the organizer, being very polite, they actually smuggled me to this tour because it was not allowed by my visa. And I remember in this tour, I was followed by 6 people. 2 people from the organizer who were sure that I will not get lost. 2 people which were probably the Chinese Secret Service overlooking for me, and 2 other people from the European organizers looking about everybody else. So this was one of the most exciting tours in my life. Going back to this, I want to stress the important role of Steven Weinberg, not just in physics and in pushing the China border to open with this amazing Mars and Bosman meeting, in which I was also honored to be a plenary speaker, but also in the same period, in '82, he initiated the Jerusalem Winter School, a new establishment which is operating at the Hebrew University in Jerusalem. And it has been operating ever since, almost celebrating the 40th year. And I'm sure that some people in the audience here have been there as either speakers or students. This is definitely one of the centers of central schools that exist today. But more important than that, since this school is not somewhere remote in the mountains, it's in the middle of a living university, this school was copied by people from other branches of science and academia. And in the same consortium today, we have now 6 different schools. In addition to physics, we have mathematics, economics, biology, computer science. Now, probably only school in the world in the humanities are operating under the same umbrella, and all this was initiated by Steven Weinberg at the time. Now, I was very lucky because just the same year that at the same '82, a few months before the Mars and Bosman meeting, I organized with Nathalie Derouel the first school on gravitational waves. This was in Les Houches, and we organized together the first school on something completely crazy and irrelevant, which is called gravitational waves. So it took some time to organize, to convince the managers of the school that this is a worthwhile topic. And we organized the school with the help of Cecile DeWitt. And then luckily for me, Cecile recommended me to Steven Weinberg to help him assist in this winter school. And I was directing and helping direct the school, being a sort of co-director or so on for the first 10 or 15 years, establishing this foundation. So actually, in one of these schools, a couple of years later, this is when one of my important, I think, works began, when we noticed that among the discussion came the idea that neutron star mergers can be sources of everything, gravitational waves, but also gamma ray bursts, and also our process nucleosynthesis, the source of the heavy elements in the universe, and also neutrinos. This is almost all the picture is there. We had one thing which was missing. This is the kilonova, and this came up 10 years later when Paczynski noticed that since you eject heavy R process elements, they could produce a mini supernova, which is called today a kilonova. So this idea came there at 87 at the school. It was published in 89 in Nature. And for the people in the audience, for the young people, I can tell them that they don't have to be impatient. This paper has exactly 0 citations for the first 5 years. Even so, it was published in some fairly recognized journal as Nature. Today, it has more than 17,000. And I'm very happy that after all these years, we have seen all these phenomena which were predicted there are really in front of our eyes with the recent detections that we are going to hear about more of them in this, this conference. So it was not exactly just because of the school. The school helped with the discussion, but this is what happens when you have international meetings. You discuss, you exchange ideas, and this is how this idea that neutron star mergers are responsible for all that took place. More recently, after that, I have with Ramesh Narayan and Reham Sari worked a lot about the theory of afterglow of GRBs. We have set the basic foundations. And this is another paper with equivalent number of citations, something like 1,600 or more. And this work laid the foundation of understanding not the GRBs themselves, but the afterglow that follow it up. More recently, in very recent work with Zhenya Derishev, we noticed that some of these basic assumptions that we had there may be not so well justified in the basic theory of the afterglow. And we have modified the afterglow. We have modified this afterglow theory. We have suggested a slightly different theory in 2016. Now, why do I mention it? I mention it because just an hour and a half ago, we heard about the fantastic observations of the MAGIC telescope with the TeV emission from gamma ray bursts. And actually, when you look at it, it's not so simple to explain the observed spectra if you look at the details. The detailed analysis of this observation, which we just published, is just confirmed all the predictions that we have from the 2016 paper. And I can tell you also that also in this talk, Razmik mentioned the other puzzling event, the recent puzzling event of observed by Hess. This theory is also, and the claim in the Hess paper, which was published in Science, that the ideas are incompatible with standard theory of the afterglow. I completely agree. They're incompatible with the simple theory that we published in the 90s, but it is in full agreement with the new ideas that we have recently. So it is really very exciting. To finish this part about the science, I want to go back to my PhD, which was about the black hole of our chairman of Roy Kerr, about, I was really fascinated as a young person by the ergosphere, by what can happen in the ergosphere. I was frustrated when I looked at the Penrose process and discovered that the Penrose process by itself, the original Penrose process by itself, the disintegration of one particle to two particles is really an inefficient process. You cannot extract significant amount of energy. Actually, you cannot extract any energy if you just rely on a particle which falls into the ergosphere and to disintegrate. So in my PhD, I was working very hard to make Penrose efficient. And the way to make Penrose efficient is to replace disintegration by collision. So we invented what is called, what we called at the time, and they call today, the collisional Penrose process, in which two particles collide in the ergosphere. And this is another idea that was suggested and completely forgotten for almost 40 years until it was rediscovered recently. And now there is a whole flurry of activity about the idea that using collisional Penrose processes, you can accelerate particles to extremely high energy in the vicinity of a black hole. And the last remark is talking about black holes. As a young person working on black holes, I was of course very excited. But then at that time in the 70s, it happened more than once that I came to some place, I gave a seminar about collisional Penrose processes or some other ideas. And then at the end of the talk, a distinguished person, I will not name some of them, will come to me and say, this was a very nice talk, very nice work, but frankly, I don't believe in black holes. I think that it is reassuring that after something like 50 years, we don't hear this statement anymore. And maybe there are still people who don't believe in black hole, but they are very shy. They don't say it so loudly as it was used to be said in the 70s. And this is one of the great development in our field. And I'm sure that with the new development, like the one that Rashid spoke about with the Rosita and other satellites, and the one that Razmik spoke about with new high energy detectors, we are going to have many more excitements in the near future, and all are happening in the vicinity of Kerr. Thank you.
Thank you very much, Zvi. I think we are coming almost in perfect time. We will send the record to Stephen. And let me take the occasion to thank everybody for this very unique morning, initial afternoon, starting with Dimitrios recalling so many important moments, even about the Penrose process, and especially to the mass formula of the black hole, which has become today a source of energy, which is, thanks to the Kerr solution, the origin of gamma ray burst, active galactic nuclei, and also ultra-high energy cosmic rays. And we have just to keep working on this avenue, which will certainly develop exponentially in the future. Gerhard Tuft was also very nice, and he will deliver the talk tomorrow. But my special thank go to Alexander Shirshakov of the Lavochkin Association, Peter Predel for the participation of Max Planck, Rashid Sunyayev as animator and participating of IKI, and the fantastic mission which is offering the view of thousands, certainly, and maybe millions of black holes in our past universe. It was also very nice to have the talk of Sunyaev following the celebration and introduce us to some of the discovery of these first days published in 31st AstroPH. But where to me, the real fundamental change in relativistic astrophysics has come from the talk of Kramer, to see how much new physics of general relativity can be extracted from binary and multiple binary system, multiple, triple binary system, and from pulsar. It's incredible. And to me, the most incredible is that each one of these constraints impose limits on the validity of general relativity, and that general relativity is passing all of them with incredible accuracy. This is really hard to imagine while we were following for years the development of this field. Also, very nice has been the new limits and the new understanding of the first black hole in Cygnus X1. To me, that is very touchy, that the criteria I followed long ago are still valid and even fortified by this observation. And there is new physics, like we have heard from Miller-Jones, but also from Mirabel in pointing to the relevance also of the magnetic field, which could be very crucial in the future. Mirzoyan Razmik has given a splendid overview over the entire field, new field, which is becoming more and more active day after day, of the TEV radiation. From a very large number of sources, but frequently. There is something absolutely new, which we are studying in this house and which is coming up with great power. But before closing, let me remember one of the key points I wanted to do is to have an occasion to recall Salam, Abdus Salam, with whom all these meetings were started. And I've asked one of the collaborators, Ashkar Kadir, of Abdus, but also Professor Bagheri, under the presentation of Professor Subhuti. Subhuti, by the way, has been one of the most distinguished collaborators of Professor Chandrasekhar, and the spirit, the high spirit of that research is present in this Nanjing Center, which I suggest everyone to go and see. And also this Bagheri lecture, which is so thoughtful about the history of mathematics and physics and astronomy, which we all enjoyed. And then let's go back a moment to Yuval Ne'eman. And one of the first person to enjoy our success with China was Yuval, who went soon after to China and promote also the diplomatic relation establishment between China and Israel which now are among the strongest in the world. Thank you for everyone and see you tomorrow. Thank you, Roy. Go to sleep.
Thank you.
You did really
Thank you.
a great job. Thanks a lot. And I see also Razmik. Razmik, thank you. And everybody else, thank you very much. Razmik, be ready to revolutionary results, Raymond.
Good night.
Good night.
Good day to you.
Good day. Good day. Okay. Bye. Soon, in a few minutes, we'll start the. At 4:30, we'll start the parallel session. 4:30 Rome time. I go to lunch.